This end-to-end machine learning course will help you with core concepts and advanced MLOps integration. IU Singh will guide you through creating a project to help you learn data analysis, feature engineering, and model implementation with rigorous testing, while also teaching you how to write scalable and readable code. Finally, you'll learn how to integrate MLOps using tools like ZenML and MLflow for seamless experiment tracking and deployment.
What if I tell you that you can build a house price prediction model and still be in the top 1% of the data science community and bag a classy data science job? I mean, that sounds too good to be true, right? But it's actually true. Most of the people say that go with a better idea, everybody builds house price prediction model. But in this video, I'll show you that how you can take a simplest project idea, but with the implementation, you can make it better than even the one which has the best idea out there. We will build an entire end-to-end machine learning pipeline, all the way starting from core ML to integrating MLOps principles like CI/CD, experiment tracking, monitoring, and much more. But frankly speaking, the 99% of the people, what do? They simply go ahead, take the dataset, import it, and then probably do some EDA just by sake of doing it. And once they have some sort of nice, sexy graphics and all those things, they simply go ahead and then do some processing, which is written by so-called gurus on YouTube. And then they simply create the project by calling .fit, and then they call .predict, and that's where the end of the project means. So even if you take the sexiest idea of your time, you cannot really have that in your portfolio or be in the top 1% despite having the nice idea. It's all about the implementation. So what we will do differently into this process? There are two aspects of it. One is core ML and another one is MLOps principle. In core ML, we'll entirely focus on, first of all, understanding data. Because when I was working in one of my company, one of my manager told me that there's no point in doing data science if you do not spend your most of your time in working on the data. So we'll spend the most amount of time in working on the data, understanding the data. I'll guide you through my thinking and decision process of why we are making such decisions or analysis, and based on those analysis, we will interpret those things in order to know what can be issues, what can be things to be done, what sort of algorithm to choose, and if we choose those algorithm, how do we verify whether that data fits for the algorithm, which is known as assumptions testing and violation, and much more into the core ML part. Into the MLOps principle, we'll integrate CI/CD pipelines, deployment, using MLflow for experiment tracking, using ZenML for orchestration, and all those things. And this one important factor which we'll also focus on is writing better code, because nowadays all the people right now in the community, they do not follow the right coding standards or the principles or the architectures out there. We'll make use of design patterns to write code and to actually use the right set of patterns in order to implement such scenarios. And all of this, which is core ML, MLOps principles, and using the right design patterns into the project and writing better code, would make this the project the top 1%. And to be honest, our several students just got their first job by just doing this. So this is the project which is a testament of implementing it right, no matter what the idea is. So let's get started with the project. Hi everyone. So we are finally going to start our series on building end-to-end prediction systems, models, using MLOps and core ML things. So the first project which we are going to start with is an amazing project, and which you all are aware of, is basic house price prediction. But the whole point of this project is to differentiate you. So how can a simple project like house price prediction, which most of the instructors on YouTube and stuff like that are teaching on Jupyter and stuff like that, how can we make it a top differentiator and get you in the top 1% just by working onto this simple project idea? The whole motto for this project is to make you believe what matters is the implementation of the project, not the idea. But of course, idea matters at some extent, but even the simplest idea can be implemented in such a way that will even defeat the top guys. So let's go ahead and tell you a little bit more about the project. I don't need to explain about the idea too much, so I'll just skim through it as much as I can. And possibly I will tell you a little bit more about the plans, how are we going to structure this project. So the first thing is, I'm not going to code it entirely. So it's like that I'll make sure that I get you each and everything implemented. However, there will be some parts of it will be working as kind of that you should experiment by your own, and you should do it by your own, which will involve as part of an assignment system also. So around 2 to 3 kind of code lines or code blocks will be left for you guys to do and experiment it out by yourself. Apart from it, we'll be also not doing live coding, because live coding into this, I wanted it to more explaining things rather than writing and reading the code. So my most of the time will go into explaining the code, will explain the concept behind it, explaining the theory behind the code, and so that you easily understand why there's the matter of the fact over there is. So the first thing is, which I want to tell you, that what this project is focused on. So this project is focused on building an end-to-end machine learning pipeline for a house price prediction system. So house price is that we will be given set of features, we'll be giving set of information about a particular house. We need to predict what will be the possibly price of the house. So that is the system which we want to build, but in a differentiated way. So we will I hope that you are already aware about pipeline stacks, because we have already learned a lot about this into our MLOps fundamental thing. So I'm not going to go deep into it, but because we have already done something with ZenML, we'll be utilizing ZenML, which is an orchestrator MLOps framework. The reason why I love ZenML is not because of me being any relation or past relation with ZenML as a team, but also because it is very easy to use tool, and it seamlessly integrates several other MLOps tool in order to build the full stack of it. That's why I love using it, and it is relatively easy to understand and very easy, simple code sort of in Python to write also. So it's an MLOps framework that will help us to manage our machine learning workflows, that okay, after this step we'll be implementing this step. So you learn a lot about the steps and stacks, pipeline, stuff like that in ZenML when we actually go ahead in the coding stuff. And then we'll be using MLflow. So MLflow is one of the integrations of ZenML2. So where we'll be using that in order to track our experiments, because we'll be doing several experiments by doing this or doing that. So we'll be using that to track our experiments. And also we will use that to deploy our model. So if you have already seen our fundamentals project, over there we were having the customer satisfaction thing. In the customer satisfaction, we also used MLflow to deploy the model. So this will be recreating of that same scene, but possibly in a different code and sort of thing, so that you know that how to use MLflow in different projects too. So that is the primary goal also. So what is this? It is basically predicting house prices based on several features. But now, if you see the machine learning paradigm, if you see data science paradigm, there are a lot of people actually doing this project. There are a lot of people who is working onto this project. So what differentiates you? What will differentiate you into this particular system? Now, I'm going to stress out on two matters on what currently people are doing. So there is very limited exploration. So what most people do is they go ahead, they start with the basic exploratory data analysis using standard frameworks. So the utmost what they can do, they will follow the frameworks which is listed on YouTube, they'll try to copy and paste those frameworks, and they do not make story out of it. They do not do anything. They just plot images and stuff like that. That's it. And then they simply they simply do not even look at those things, and then simply go ahead and call dot fit on a model without thoroughly understanding the data. Data science is where data is an integral part. If you do not spend your most of the time into it, that means you're not a data scientist. And one of my manager, when I was working in one of my company, and he was also director of ML at IBM, he told me that there's no point in learning data science or machine learning if you do not know how to work with data or how to understand data. So we'll be spending a good amount of time into it. Now, another people, most of the people do, they simply split the data, train a model, call predict, evaluate the model, and they often tends to achieve the high accuracy and or minimizing any sort of error. That is their whole motto. But they don't understand the fact that in an organization looks for an overall robust model, and for sure that okay, even if you have 60%, 70% accuracy, that accuracy is being maintained over the period of samples. So that is another problem which I see. Another problem is if the student has completed the project and the model is trained, that they rarely revisit or improve based on deeper insights from the data. They do not spend their time in validating assumptions or handling violations stuff of the algorithm and stuff like that. So this is a major problem which I feel that do not take. I mean, if if a lion eats a fresh meat, if you give grass to it, he will die, right? He will not eat. So that is what into the same example, that if an algorithm expects some sort of data, you should only give that data, because that is the assumption that if you give me this data, then only I'll work. Otherwise, I won't. So that is another effort. They do not put in effort. And we have also done a lot on validating assumption in our core stuff. So I want you to go ahead and look at it. So we'll be doing all of this, but what we'll be doing is, again, what I told, that thorough data research. Will spend a very bit of time into understanding our data, and we'll try to see if we can possibly use that to make a storyline, and based on the storyline, how do we make decisions to go ahead and build our models on top of it. Apart from it, we'll not just be training a model. We'll not just, training a set of dot predict, dot fit, and stuff like that. We'll be also doing that, but also will ensure that we are not going ahead in just core ML thing. We are also ensuring the assumptions, refining it iteratively, and also implementing robust pipeline, which is reproducible and deployable. So, which is an MLOps integration to it. And that will make the project the top 1% project ever created. And I feel this house stress prediction will be ever being created on for students to actually see how it can be done differently. And what I told, that we'll differentiate our project integrating MLOps practices using ZenML and MLflow. We'll implement CI/CD pipelines to automate testing, deployment of the model into production. So there will be several tasks like that. You have to take the API, you have to integrate with this Streamlit, you have to also test other assumptions, because I've not tested all assumptions. Few assumptions were tested to make sure that it works, but there are several other assumptions to test, several other models to try. But one thing I want you to know for this project is that we'll be only utilizing only one algorithm for this project. We'll be not switching the algorithms out there. However, there will be tasks for you to implement other algorithms and then intelligently switch between algorithms and then use that. It is pretty easy. So we'll be utilizing, because our main focus is that I want you to know that how can the project be implemented with a single algorithm, with the core basics, and also being even the simplest but even the powerful project of your whole portfolio. So I want you to take a look at this in greater detail, and if there will be a lot of errors for sure, because MLOps is still has not matured enough to have its own community. So I want you to be available in MLflow communities, ZenML communities, Slack community. You can also use Piazza to ask a question if you're enrolled into the course, and try to see if you can possibly get the answers of it. But MLOps, as I say, is not matured enough. What does it really mean is that you do not have the support systems ready. You do not have the support practitioners ready into it. So over here, you need to put in a lot of your mind, but eventually it works out. You just have to stick to it and make sure that you do not go away or, feel depressed from it. So that is it about the project. Now, our next thing would be that I will tell you about a plan, what exactly I'm looking at the plan of this project, how I'm going to take this project from EDA, ingestion, what are the source which we're going to have, how are we going to deploy the model. So I'll tell you a little bit about the plan, and then we move it further. So let's meet in the next lecture. So now we will go ahead and then I'll let you explore a little bit about the project, what exactly the project folder looks like, and how are we going to move ahead. And then I'll teach you, before we start anything, we'll teach you 3 design patterns which we will be using a lot into this project, because as I say that I want to make it a very big differentiated project, and for that I need to have this specific and proper set of modules listed out here, proper set of documentation being done. So all those things will be doing it. So first of all, we will go ahead, learn a little bit about the design patterns like strategy, template, factory, and then we'll start with our project coding step by step. However, there will be some of the stances where I'll state you that you should do this by your own, or you should try this by your own. So please make sure that you note all of these things down, because as I say that I'll be focusing more onto the explanation part of it, and making sure that you understand each and every line of code in detail, and my mindset and the thinking beyond it. So that is the whole goal. And I also like live coding, but live coding into this will not make sense to me. So probably my main focus into this project will be to explain you each and every details about the project and let you explore things by your own too. So let's go ahead and then study a little bit about our first thing, what exactly we are going to do. So first of all, we will always focus on loading the data. So any project you should start with, you should always think about once you have the data, because I've taken it from Kaggle, because as I said, it is a very simple project, which is house price prediction project. So the first step is that how do we ingest the data? So most of the people, what do they do? You get the data in zip file, and then they simply go ahead, write a function, or probably in a Jupyter notebook, they use pd.readCSV, first unzip it, and then they do the read CSV, and then that's it. We'll do it very differently. And that's where very small things attract the recruiters or the interviewers to make you think, okay, this guy has done something really interesting. While I don't want to go in detail about what design patterns helps, how it helps, and all those things, but in a nutshell, it's more about making your code reproducible, scalable, understandable, and very easy to maintain. So that is why we use design pattern. And we'll be using one of the factory design pattern to implement the ingestion function, or probably implement the ingest data pipeline. So before we go into the code, I want you to know a little bit about factory design pattern. So what is factory design pattern? Factory design pattern is, let's say you have a coffee shop. So you have a coffee shop and customers can order different types of coffees into it. It may be espresso, it may be latte, cappuccino, frappuccino, whatever it might be. But the process of making a coffee follows a similar pattern that you want to put it, of course, let's say milk or skimmed milk or whatever you put it, maybe some sort of coffee powder. So the process of making those coffee follows a something similar pattern, except some of the coffees. So now you have a general coffee making machine. You don't have several other coffee machines like latte's coffee machine, cappuccino coffee machine, or frappuccino coffee machine. You just have one simple general coffee making machine. That's what we call as a factory. And then into that factory, you make different types of products or different type of coffees, which we name as espresso, latte, or cappuccino. So what we do, let's say that we want to code our thing, that we want to make a coffee machine, and in that coffee machine, we'll be having several other coffees out there. So I'm going to show you, you can simply go to the folder and click on explanations and click on factory design pattern. So over here, I really hope you're able to see this screen. If not, I'm just going to zoom in. Yep. So over here, you will, I want you to, if you want to know more about the design pattern, I can come up with that course too, but it's just that you can just go on YouTube. There are a lot of courses available on explaining about abstract method, OOP concepts and all. But in a nutshell, we first of all create a factory, which we call as a product interface, or the general machine. So general machine would be coffee, and that coffee will have one of the implementation, which is to prepare the coffee. So a coffee machine will have one of its function is to prepare it, right? So any coffee, let's say latte or espresso, needs to go through that preparation stage, and then only the coffee will be built. So in the same way, a factory like a coffee into this, the name of the factory is coffee, will have its own will contain the preparation stage too. Now, once you have factory, you can extend that factory to multiple products. You can use that factory to create concrete products, create several products out there. So that is what class espresso. And then espresso will be built from what factory? Coffee factory, because espresso is kind of a product which will be built in the coffee factory. And then we just implement the prepare. So of course it does not have any logic. It says preparing rich and strong espresso. So you simply on top of it, you use the prepare method. You can also add multiple methods over here too if there is any specificity needs to be maintained. Same goes with latte, which inherits from coffee, the prepare method, and then same goes with the cappuccino, prepare. Now over here, you make a actual factory class. So actual coffee machine. So the coffee machine is like coffee machine and the make coffee. And what is the coffee type? The coffee type is espresso. You just call espresso.prepare. Espresso.prepare. If the coffee type, of course, you see that we are using the coffee type. So I'll show you the usage too. So it's more like that we prepare the factory with different products. So if the coffee type is espresso, you prepare the espresso. If the coffee type is latte, you prepare the latte and stuff like that. And then now here's what the usage of the factory to create products. So it is our factory. Of course, now you might be confused. It is our factory or this is our factory. In most of the cases, this is the practitioners follow. This is the interface which they create, but also I have seen people using it directly from here. But to create that extensibility and readability, they actually create another factory where this acts just like an interface. There's nothing else. It's just an interface that this is how it should look like, and then you implement those interfaces. For example, into the design, you first of all have that design thing ready, and then the developer goes and implement by seeing the interface. The same way it happens over here, that you create an interface first, and then you probably go ahead and create the concrete products or actually develop it. But yeah, it totally depends on you on how you want to extend it further. But the general practice is to having these factory sort of pattern. So the factory pattern will look like this, that you create a class. Now that factory will have one of its preparation stage too. The preparation stage will look like, I want to make a coffee. And what is the coffee type? It expects the coffee type in an input. And then whatever coffee type, if there's no coffee type, then it returns an error. So if we instantiate our class and factory class, and then we start to make coffees. So we create a coffee and then machine.make coffee, which is espresso. We want to make espresso. So espresso is the type. So it calls the espresso concrete product, one of the product, and then it calls .prepare. So if you see that we are also calling .prepare method from it. So and then outputs are preparing a rich and strong coffee. Same goes with the latte. You just need to put in your coffee type, and then you get your factory design pattern out here. So I hope that it helps to understand a little bit about what exactly factory design pattern means. Now what I'll do, I'll simply go ahead and teach you a little bit about how we use this factory design pattern into ingesting our data. So I don't want you to look at any of this. I just want you to look at few folders. And of course, you have to do it again by your own. So by the end of this, you don't have to write it from what I'm teaching. It's not on the way. I want you to first of all see, understand, and then do this project from scratch by your own. So I want you to look at the data folder, and the data folder is having archive.zip. We'll be giving all these files and folders into our source code. So if you're a paid guy, then you must be having these things already available to you. If not, please feel free to ping on Piazza or tell to our course instructor, course coordinator. He or she will be able to help you out. Now, into this archive.zip is where you have the data available. Now, most of the people, what do? They simply create a function to unzip the file and then probably go ahead. Now, let's understand a case where there is CSV file. Then what you need to do, you need to create another sort of folder, and then the different type of data comes in to create another function in the same file and then try to do it. And then what if this JSON things comes into play? You're going to create another function into the data ingest. Now, that is the readability and probably very messy and not extendable code. If you have 1 million formats of the data, are you going to create 1 million stuff? Of course, you have to create functions for every. You'll be not doing it because it is, if you think about in terms of time complexity and stuff like that, it's not good. So what do we do? So I want to look at ingest data.py, and the way we work into ingest data.py is we going to implement the factory design pattern into this. So what happens? I'm going to be very honest. So what happens that you will be having the data coming in, and then that factory will have one work, identify the format of the data, and then ingest it. The pattern is very similar to it, but the factory remains the same. Factory can produce several formats. Factory can ingest several formats, right? So this is why we are going to use abstract class into it. So sorry, factory pattern into it. So as usual, we have created our own data ingester interface, or interface for the data ingester, of what it will look like. So the interface would more like that we want to ingest. So every implementation of this interface will have, every implementation of any format of data will have ingest method. So ingest method will take file path, that what is the path of the file, and will return the data frame, because we always work in a data frame. Of course, there's several other formats, but into this project we'll be working on data frame. So over here, that will take file path, and the file path type would be string, and that will return the data frame. Now, why I am highlighting these, that what is the type, what is the returning, and adding the doc string and stuff like that. The reason why we are doing it, because if anybody comes and sees this, they know that if I want to run this class, this will return a data frame. That's what it is going to be returning. And then this is what we call as type check-ins. So over here, you are telling any developer which is coming. So that maintains the readability of the code. And that is what most of the organization look out for in your code. So now as you move forward, we want to implement because our data is in zip file, we want to ensure that we have the class which takes in the zip file and then possibly unzip it and then converts into CSV file and then returns the data frame. Now, zip data ingester will take an interface. That data ingester is an interface that you should have ingest method. Now, that is an abstract method. Abstract is what? Something which is an imaginary thing, right? So that is what imaginary thing. Now you have to convert those imagination to implementation. So ingest data will expect a file path and return the period data frame, which is extension of this ingest. And then now we go ahead and ensure that the file which is coming in is a zip file. This is another important aspect of it, that we want to ensure whatever coming in. So even if we have given it, we want to ensure the file is a zip file. If the file is not zip file, we want to handle that error and raise the value error saying that the provided file is not zip file. Now most of the people, what they will do, they'll simply go ahead and extracting the zip file, but they will not verify that things which is coming into me is really a zip file. Then only it will work. So this is a trait of a professional developer or a data scientist or machine learning engineer, that they make sure that whatever coming in is perfect for it to work. Now we are going to use a zip file library. So zip file is a library which helps you to extract. So on zip file, we give file path, we give access to read it, and then we say extract all the data from it. So it simply extracts the zip file. And then once the zip file is extracted, now there is the CSV file which is into the zip file out there. So now if the CSV file is not there, that's where, so this is the CSV file. So we want to ensure that there are CSV files. So when you list the directory, so OS is where you can list the directories of extracted data. So there will be another folder created, extracted data, and the extracted data will have, so it's like zip file, you give the zip file path as a zip reference, and then you extract all into the new folder which is extracted data. So it will extract whatever content is inside it. The content is mshousing.csv. Now that is the content into that particular zip file. Now you just go ahead and then look at the files which is present inside the extracted data, and then what you do, you see that if you have this kind of a one-liner thing for f in the extracted files, if there is the files available which ends with .csv. If that is, then you simply go ahead. So it's like we handle another error. So we'd say if length of CSV files, whatever length, if there is 0, which means no CSV files are found. So we cannot go ahead and help you out into this. But also we also handle another case which says that if the length of the file is greater than 1, which means there are multiple CSV files found, please specify which one to use. So if there are multiple files, you handle it differently. So we look at both of these things, and then we go ahead and then we join the extracted data. So we create that path so that the path will look like this, that it goes extracted data / your CSV files. So I wanted to, this is the basic things which everyone should know. So it's as simple as that. And then once you have the path ready, you just call read.csv. That is the power of doing things very differently. So over here, we have learned several things right now. The main motto for you is to figure out when you work on your project, these things should be key element of your project. Is type check-ins, readability, handling errors, making sure that we are handling errors. And fifth rule, do not forget all 4 rules out there. Okay, perfect. So now what we do, because we have the zip extension, we have zip product ready, we simply go ahead and create the factory. It is a static method. And of course, I expect you that you already know static method, abstract method, because it is the basics of Python to be learned. So you say get data ingester, and what is the file extension? And then it will return the data ingester class, which is this class, which is the abstract class. That is the type which we want to have. So this is a kind of type which is being returned. So data ingester, it expects the file extension, and then it goes ahead and then ingests the data. Now, if the file extension is equals to .zip, then only run the zip data ingester, otherwise do not run. So it said no ingester available for file extensions, let's say JSON. So now let's say if somebody who needs to create the JSON, they can just extend this abstract class to JSON following or writing the implementation of the ingest. So this ensures your readability and ensures your scalability aspect too. Now the usage is, I'm not going to run it because I'm going to show it you in Jupyter Notebook as soon as you go. It's more like this is our file path. We take out the extension by looking at what exactly the extension is by following this, determining the filing extension. And then over here you are seeing we're not hard coding it. We are actually using that to figure out using the coding and then that .csv thing. And then we getting the appropriate data ingester. So if it was CSV, so now that's another learning for you. The learning is that if by chance, if it is you have millions of formats, and over here you have JSON. So every time you need to change this file extension, so what you do, you automate this process by looking at automatically over here, and you just pass in this variable into this. So it automatically gets the extensions just by giving the file path. You don't need to change file extension every time you go. So ingesting the data and loading into the data frame, which is ingest, which is the data ingester. It ingests the file paths, and then we print the data df.head. I want you to run it by your own. I'll be also running it in Jupyter Notebook right now, but this is what the ingest data looks like. I hope I was able to explain you very clearly about how do we ingest the data into this and several learnings from it. And now what we will do, we'll go ahead and spend an hour or so, or probably less than that, 40-50 minutes into the EDA, which is exploratory data analysis, and we try to understand our data in a very detailed way. Before we get started towards doing more analyzing and stuff like that, what I want to introduce you to, it's something known as Julius. So Julius is something which I use a lot because it helps me to analyze my data better, and they're doing very well and very good community work, and something which I'm particularly very used to in my projects, and helps you to give an overview and work towards creating more better and understanding your data better, right? So I want you to first of all go to Julius AI, because Julius AI is something you can go here. It's more sort of analyzing your data. So it helps you to analyze your data, gets insights, do advanced analysis. You can also help ask it to do problem solving and stuff like that. And more interestingly, you can develop reports. So something like this, which creates a very big differentiator. So we have not utilized this whole into the course, but I want you to utilize this by your own and possibly see what you can do with it. Like you can do visualizations, you can ask data questions, you can do some quick experiments you want to do. You can try to set several set of models by one liner. Of course, it is not replacing it, but it is helping you to make your task easier. That's what employers wants to see. They wants to see you whether you are able to use kind of a quick things to understand and save time in your original work. So this is the Julius, and I want to show you some of its interesting feature because I use it very regularly. Is what you can do, you can either go ahead and create a new thread, you can upload your data, the house price data you can upload simply over here. and then you can start asking it more formal questions. But at the same time, what I want is I want you to see something known as threads, which is you can just go ahead, upload your data or Google Sheets or maybe some stuff like that. You can start with data visualization, or probably they have a lot of workflows. So I wanted to go to the my workflows, and then they have a lot of workflows. If I could show you, um, uh, just give me a second. I need to log in it. Yeah. Explore workflows. If you go to explore workflows, there are a lot of workflows which is available out here. For example, data processing, data visualizations, data cleaning, statistic, bar chart, education. So let's say that you want to explore some visualization. You go over here, and there are a lot of workflows already available for you. So you don't have to create by your own, but it's already available for you, like correlation matrix, grouped bar, are probably simple in creating correlation, principal component analysis, Friedman tests, and much more. So let's say that I want to go ahead with the correlation matrix. I click on the correlation matrix. So what is the steps? So it asks you to upload the data, and then it will give you the correlation matrix chart. So let's say if I visualize it, so it's more like you run the workflow, and then you have to upload your data first of all, because that's what it asked for, is please upload the data. So you upload the data, and then you ask any sort of task, and then you execute this, that it will automatically create a correlation. So this just like this, there are a lot of into the data visualization. Same goes if you want to do data processing. They have workflows over here, which is combined to CSVs, and they are coming in a lot of workflows to make your experiments quicker. So you can start with all the core things over here itself and get things done. So this is what I use very often, and they have a very nice community forum and probably model lab, and you can explore. The community forum is too good that you can get a lot of suggestions on your projects, which I personally use. So I would suggest you to utilize it as much as you can, and then probably see. It's completely free tool. There's no, I'm not doing any paid promotions and stuff like that. It's completely free tool. I use it personally. I want you to use it. So yeah, let me know. I want you to utilize this, but of course, let's get started with our original thing, which we have started to do. So, hi everyone. We are finally going to start with analysis, one of my favorite part, and possibly I could say that one of the most important part into any project. And we will not just follow a particular framework. We'll not just follow a set of that we should do this, do that. I'll show you that what was my decision thinking involved, what was my mindset before applying any sort of visualization or sort of plots or any as such. So I'll show you those decision or mindset thinking, so you develop a practicality of what EDA is about. EDA is not about following a standard frameworks and then looking at it, that's it, for the sake of doing it. But actually it is important because it helps you to understand what sort of decision which I should make when I go into processing stage, feature engineering stage, because you'll be noticing that I'll be taking several insights from EDA in order to decide which algorithm I should use, decide the feature engineering, decide what sort of processing techniques needs to be applied, and much more. It also tells me a little bit hint about whether my model fits the assumptions for the algorithm which I'm going to use or not. So we'll spend a bit of time into analysis and make sure that you fully understand it. And again, I want you to open up the documents and everything materials so that you also follow me along. Now, over here, imagine before going into our EDA stage, I want you to first of all teach a little bit about strategy pattern, and probably I'll teach you why it helps, where it helps, and stuff like that. So strategy pattern is another design pattern. So let's say that you're developing an e-commerce application. So e-commerce application is where you create some sort of payment gateways and all. So customers can choose different payment methods like credit card, PayPal, Bitcoin, Google Pay, UPI, stuff like that. So each payment method has a different implementation, but the overall process is the same, that the customer has to pay. So the process or the context remains the same, that they have to pay, but the strategies differs. But the strategy differs because sometimes they use credit card, sometimes they use PayPal or Bitcoin. So over here, we create a strategy, which is the payment method, which is an interface, just like we were creating into our factory, that we create an interface that it should look like this. And then we create several strategies or implementations of those payment strategies, that credit card payment, PayPal. You develop a logic of it. And then you have the context that everyone needs to pay, that they need to put into a context that will be used to pay. So the context is that everyone needs to pay. So the process remains the same, but the implementations differs. So I'm going to exactly code this out into one of the explanations. So I want you to go ahead and click on explanations and click on strategy design pattern. So strategy design pattern is probably same as what you have been doing in a factory design pattern, but it again has its own advantages and powerful stuff, which eventually you can use it into a project and which we'll be using into the EDA part 2. Now, the strategy design pattern will have its, first of all, a strategy interface, which we call it as a payment method. So strategy interface will have its own method, the abstract method, the imaginary method that every strategy should implement this method, which is pay. Now, pay is where it is abstract method. It takes in the amount. You can also go ahead and typeset. It's like string or integer or whatever. Now you take that as an interface and implement strategies. It might be a credit card payment, or it might be you inherit that abstract class and then you into the concrete strategies. So payment method, PayPal, Bitcoin, UPI, you can create multiples. And then you create the context. The context is the shopping cart that everyone needs to pay. So what sort of payment method, and then the checkout method, so which is dot pay, which is everyone needs to pay into the context, into a particular shopping cart. So you go ahead and create the shopping cart, the strategy, what sort of payment it expects, and then you pay card.checkout, whatever the number is, card.checkout 200 for any sort of payment methods. So this is a simple explanation about strategy design pattern. And we'll be using this into our EDA or analysis, because see, the EDA is over here. I don't want to look anywhere. I just want to look at this analysis folder. So analysis folder has eda.ipnb, which is Jupyter Notebook file. You can use Jupyter Notebook into this case. I use Visual Studio Code because starting from 4 years, I've been using this only. So I particularly like this using into the Visual Studio Code itself. But what you can do, you can also do it on a Jupyter Notebook, whatever you have. Now, before getting into this, I want you to be very comfortable with what this folder indicates. So analyze source is the implementation. So we'll be doing several plottings, visualizations, several other things. We have like data inspection, missing value analysis, bivariate analysis, univariate analysis, multivariate analysis. So if you do this, this will be very cluttered. I want it to also be scalable so that anyone at any point of time can use this. So for that, I have created analyze source where all the implementations and the logic present in the source file, and then EDA uses those source file in order to create visualization so that it remains very small, right? Kind of a Jupyter Notebook, because I'm not a big fan of implementing logics, because Jupyter Notebook, implementing logic in a Jupyter Notebook does not make you a big differentiator. So over here, we'll be having the analyze source, and all the implementations are done into the analyze source itself. Now, if we go ahead and look at EDA. So EDA, I want you to first of all ignore all of this, whatever the imports we are doing. Just remember import pandas as PD, import numpy as NP. And then because we have already extracted the data, because I actually ran that ingest data, you also have the CSV file. So we don't want to use that directly over here. We just can use the CSV file which has been extracted, and then pd.read CSV. So it assumes that you have already extracted the data into the extracted data folder from the zip file. Okay, so now once you have loaded the data, you also set the display options that you want to display maximum of 100 rows to make sure that it looks very beautiful into the Jupyter Notebook. That's why we just have the display options for the data frames and stuff. So the first step is any project that I want to know about the data. I want to know how many number of rows, how many number of columns, what is the basic numerical things, what is the mean, median, the number of accounts, standard deviation, variance, and all those details. I want to know each and every aspect of that. So I've created a basic data inspection.py, and a basic data inspection.py, what it does, that it does the basics of whatever inspecting of the data is. You can also copy the same code into several other projects, because I've done a spend a very good time into documenting it out very nicely, so that even if you just go ahead, you know each and everything just by looking at the project itself. So when you move ahead, you have the abstract base class for, so as usual, you'll create an interface that a data inspection strategy, and the work of it would be to just inspect. And how it will inspect is by taking the data frame into it. So the general format, so this is another learning for you. The general format for writing any doc string is as follows: that you write a one-liner description about what exactly this method does, what are the input parameters it takes. Into this, it is taking a df, which is a data frame on which the inspection has to be performed, and what is the type you mentioned over here, and what it returns nothing, because it is an abstract class, right? And then you just pass it out so that you don't have to you're not implementing it. It is just an abstract base class for your inspection. So I've also written this class defines a common interface for data inspection. Subclasses must implement the inspect method. So if you implement another data inspection strategy by following this interface, they should implement this inspect. That is where your strategies come, because as I say, the implementations might be different, but what do they have to do? They have to just inspect it. Right. So now, as you go ahead, we create a simple one, which is the data inspection strategies. So we first of all explore the data types of each column and count non-null values into it, which is basically df.info, which you guys do. So again, you're seeing even the simple df.info could have been done over there. It has been elaborated nicely, which shows your readability for anyone coming over here. Right? So it shows data types and non-null counts for every column. And then another strategy, which again, summary statistic inspection strategy, which is one of the subclasses of your abstract class, which is data inspection strategy. And then over here, you create an inspect and then takes the data frame. What it does, it prints the summary of it. It prints the summary statistic of the numerical columns, and then it inspects for the categorical columns. So both of it we have printed out. So a simple thing has been converted into a very nice set of subclasses, which again makes sure that we are not complicating it. This is what is being done by most of the people out there, good people. So now, because as I say, into the payment case, the shopping cart was the context. Into this, the data inspector was the context. So what it does, it helps you to allow to switch between different data inspection strategies, because one way is data types inspection strategy. Another one is summary inspection strategy, right? So it helps you to switch between several, just like in the shopping cart is able to switch between credit card, PayPal, Bitcoin. Over here, it happens the same. So it expects you to tell me what strategy I'm going to use, and then it just takes in the parameters of the strategy to be used for the data ingestion. And then it sets the strategy, what sort of strategy needs to be implemented, and then it executes the strategy. So we create a self.strategy, and then we set the strategy by the strategy given into our input, and then we execute that by calling the strategy.inspect, because one of the method is .inspect from this, so we just call .inspect, and then we give into the data frame into it. Very simple. You just go ahead, and that is what the whole thing is. So now if we go ahead to eta.ipnb, you simply go ahead, you import the CSV file. The first step is data inspector. So you put in your data types. First of all, you want to understand about the data types, and then you click on execute inspection, which is call execute inspection. So when you call execute inspection, what it does, the execute inspection will simply go ahead and then call this strategy.inspect. So strategy which has been set, it will just simply go here and then call this method, which is the subclass method, and then that will be run, right? So over here, when you run that, you'll be having what is the entries, what is the columns out there, what is the non-null count, what is the data type of it. So all of this, you have 81 features out there. Of course, you cannot see it everywhere, but yeah, that is what you can see. Now we will come back to this once again because there are 89. We need to find a way that, because we cannot just keep on looking at non-null, we are going to find the specific ways to see where we have a missing value. So that's why we have missing value analysis systems ready to. But now we also want to switch our strategy to summary statistics. So instead of instantiating the same method, we just change that data inspector to set strategy to the different strategy, which is summary statistic inspection strategy. So we do not have to reinstantiate it, right? So data inspector again dot execute inspection, it just goes back to summary statistics, it's calls the inspect method and then prints out for you for the numerical and categorical columns, right? So this is what you get in the inspection. Now, what we do, we build a storyline out of it. Now what you can do, you can simply go ahead and click on open into view as a scrollable. So now what you can do, you can explore all these columns out here. And same, you can just go and click on scrollable element. You can go ahead and look out for the detailed summary statistics for the categorical, summary statistics for the numerical. Now I want you to understand a storyline behind it. I want you to know about the storyline behind it. So let me tell you what is the insight which I gathered. Of course, you can take a brief look at the data and then come to these insights because I've already taken a look. I've written that out into the markdown. So the data set contains 2,930 entries and 82 columns, which is very simple to understand. And there are 11 columns with this, 28 columns with this, and this. This is a very basic, whatever insights which we could get. Now, this is the major insight from the summary, that it tells you a lot of stuff out here. Now, the first one is numerical feature. So in numerical feature, the target variable, the sale price which you want to predict, that is the target variable which we are targeting because there's several features and you finally have to predict the sale price, has a mean of $180,796 with a standard deviation of 79,886, which is indicating a significant spread in house prices. Like there is significant, if you know what standard deviation, that's, I hope that you're able to get it, that they're spread throughout it. Now you'll see when now over here there's another decision that how it is spread. That is another question. Is it too low or is it too high? Is it positively skewed or negatively skewed? So all these things you have to figure out. That's one decision which I made, is I want to go ahead, see what the distribution of sale price is, because I want to know, because it is showing a significant spread into the house prices, because mean that is, and standard deviation 79,000, which is huge for the significant thing. Another one is overall quality, which is the quality of the house, which ranges from 1 to 10 with a mean of 6.609, which is showing a relatively high quality and average. And then what is the year built, which is 1872 to 2010, indicating that the data sets includes both very old houses and relatively new houses into the data set. Lot area, which is the kind of area which is there, has a wide range, which means that it says that there is a maximum of 215,245 square feet, which might indicate very large properties. But there's also concerning, because if you're using linear regression or any such algorithms, there's several regression algorithms which is very affected by outliers, and they can potentially overfit and they can potentially ignore these kind of values. So first of all, it indicates that there are large properties, but it also says that there are extreme outliers too. Because the mean is 180,000, it is getting lot area is 215,000, which is huge, which is a good big houses, but also at the same time extreme outliers. We need to look at this aspect too. Another aspect in the numerical feature, the distribution of GR live area, above ground living area, which shows a mean of 1499 square feet with a wide range, which could significantly impact the sale price. Again, we have to see the distribution of these numerical features very in detail in order to get any resulting outcomes. But what I really understood from, going ahead and then possibly roaming around and see what exactly it helps and all, I feel that we need to look at the distribution of the sale price, and also I need to look at the distributions of other numerical features, and I need to handle outliers at some point. So these are decisions which has been made. That is what my mindset is, that it tells you something, then you explore it further. For the categorical, neighborhood has 28 unique values, with names being the most common, supporting some neighborhood might dominate the datasets. So over here, we are ensuring if there's an imbalanced class dataset problem. MS zoning is mostly RL, residential low density with 7 unique zoning types. Alley has a high frequency of missing values. That's where I will come back to missing value analysis, but Alley has high frequency of missing values, which we need to look at. Now, there are other categorical variables which is good enough, but we need to ensure that those will be crucial in predicting the sale price. So we also want to look at those aspects too. So this is it about the data inspection, the basic data inspection. We have understood that there is a problem of outliers. There is a problem of missing values. Because there is a problem of skewness, we want to ensure, because the algorithm which we're going to use is very prone to, does not perform so the data is highly skewed or has a good set of outliers. So we want to ensure that we also make sure that it fits the best to the algorithm. So the next what we want to do is we want to go ahead and see the missing values, see where it helps, see the impact of the missing values, and then possibly we will see that how we could handle that. Once we see the missing values, we'll also go ahead and then understand the single variation, single analysis, like, well, the distribution of the sale price, distribution of several numerical features where the skewness is high. And then we'll see that how two features relate with each other. Are they really affecting, or are they following some sort of distribution? Right. So all those things we will do it. So let's catch up in the next one. Hi, welcome back. So we'll continue our analysis work. And before analysis work, I want you to again learn about one last design pattern, which we will frequently use into our sessions, is template design patterns. And then I'll teach you a little bit about missing values, and we'll try to decode the missing value analysis. So what is template pattern? So template pattern is another design pattern. So the analogy is the best way to understand any design pattern is try to think from a real world analogy. So what happens that, let's say you run a restaurant with a set of menu for different cuisines, each cuisine like Italian, Chinese, Indian, Pakistani, whatever. So each cuisine will have its own sequence of courses. Start with the appetizers, then main course, then dessert, and then beverages. So the sequence is a specifics to each and every cuisine. So, but the dishes, Chinese dishes might be different, Pakistani dishes might be different, Indian dishes might be different. For example, in India, we have starters, beverages, and stuff. But in starters, you might have some else, but in China, but in Chinese dish, your starters might be different, or Korean. So it depends heavily. So the sequence for serving the course is the same, but the dishes served at each step vary depending on the cuisine which you're having. If you're going to a Korean restaurant, the dishes will be different. If you're going to Indian, the dishes will be different, right? So it depends on the cuisine which you're targeting. So let's say there's an Italian meal. The appetizer might be bruschetta, the main course would be pasta, dessert would be tiramisu, and beverage would be glass of a wine. In Chinese, the appetizer could be spring rolls, main course would be noodles, dessert would be cookies, and the beverage would be tea, right? So if you notice that there's a particular overall dining sequence is the same. That is the template. That is the same. But the things which is customizable steps are the specific dishes served at each stage, which changes based on the cuisine which you have. So it's more like the template pattern which you use is more like your changing having the overall sequence, but having different set of steps. So I'm going to show you, which is the template design pattern. So template design pattern over here, the interface will be a little different. So interface would be this dining experience, and then dining experience will have to serve a dinner. Serve dinner is first serve appetizer, then serve main course, then serve dessert, then serve beverages. So the template method defines the skeleton of the dining experience, of what the skeleton should be. Now then you abstract method for each serve course, because appetizer might be different. You might be giving another appetizer, you might be giving another main course depending on the cuisine out there. So then, based on the abstract class you have, you create concrete class that implements the Italian. So for the Italian, if somebody chooses Italian, so you actually, this is a subclass of your dining experience. You serve appetizers, serving this, serving that, serving this. This is for Chinese, and then you can simply go ahead Italian dinner. So this is Italian dinner dot serve dinner. So it follows a specific course, right? The same goes with the Chinese dinner out here. So this is known as the template design pattern, which we're going to use some sort of into our missing value analysis. So we, in the last one, we have actually seen those things. Now what we're going to do is going to see if there's any missing values into it. If there is, then how we could possibly look at it. So we first create, so anywhere you should always have a plan, right? So the abstract class is more like a plan or kind of a template. So into this missing value analysis template, this class defines a template for missing values, and the subclass will have to implement the methods to identify and visualize the missing values. So that is what the plan for missing value analysis. I want you to also look at these doc strings in great detail once you finish this lecture, because there are a lot of things written in order just to understand. Okay, so the analyze will follow two steps: identifying the missing values and identifying the visualizing the missing values. So they will call two methods. The method would be you have to identify the missing values and visualize those by taking the data frame in. So we'll create a simple subclass, which is the concrete class for missing value identification, and then over there he will also visualize it. So it is a subclass of this missing value analysis template, and then it has to make the identify missing values and then visualize missing values. So into this, it takes in the data frame in, and then it says that, okay, I will missing values count by column. So it's df.isNull.sum. I hope you know it. It's simply, it creates a column, and then it, for every column, it has the number of, if it is 0, then it does not print. If it is more than 0, it prints out over here. Another one is visualizing the missing values. So I'll explain you what exactly it does. So the first step is that we want to make a figure. So we take a page, right? So it creates a figure of 12, the figure will be 12 inches wide and 8 inches tall. That is the size of the plot should be. You can also play it around if you need a little bit more. And then you're going to use Seaborn library. So we import Seaborn as SNS and use that to create a heat map. Heat map is a library where we can look at the, correlations, missing value analysis, a lot of things we can look at from here. So the heat map will contain df.isNull. So it creates a data frame of the same shape as df. So it will have the, same shape. So it will be more like, let's say the data frame is A. I'm just going to write it A 1, 2, 3, 4. Then you have B column name. Again, you have 1, 2, 3, 4, right? So now over here, this is the data frame. Now let's see if this has a none value, this as a none value. So it will, the df.isNull will create a data frame something like this. So in non values, if, so it will create A, I'll just copy and paste it directly. It will create this data frame, but there will be slight difference. It will with the Boolean value. So if the missing value is present, then it will write true. But if the missing value is not present, it will write false. So it will return something like this. It will return something like this data frame. So your heat map will be built on top of this data frame, right? So you give in this df.isNull, it will be a data frame where it will indicate stuff. Now C bar is equals to false. So C bar is in kind of disables the color bar on the side of the heat map. You can try it true and see how it works, but C bar is more used when you have the binary data sort of thing, but it is not, but it will not add any sort of information. What is the color map? The color map of this C map should be Verdis. So what does Verdis means? It will be like a which it is like a color gradient which starts from the purple to yellow. So if you have the in a particular column, if that is looking purple, then there's no missing values. But if it is yellow, then there's some missing values. So I want you to go ahead and see it. So now what I'm going to do, I'm going to simple value analysis. So over here, we are also importing it. If you truly see from analyze source to basic data inspection, we are importing this data inspector class, data type inspection, summary statistic. From as value analysis, we are importing simple missing value analysis. So we import that, and then we give the we call the analyze, and then it gives this particular column because we print it out to identify those, and then it gives this heat map too. So the heat maps over here, you can see the purple is where there is no value of no missing values, but whenever there is yellow, there are missing values available. So you see the lot of columns which has a lot of missing values available out there. So there are a lot of insights I have written. So over here, yellow represents the missing values. The more yellow the column is, the more the missing data into that. And then purple or dark color represents the non-missing values that indicate the most of the data is present if there's purely purple out there. Right, so there are a lot of columns which like lot frontage, mass winner area, garage, pool area. They all have the substantial yellow kind of. So they have the sort of missing values. Another one is that if the yellow, so there is two, I want you to know about the randomly distributed, because nobody knows about it, because I was also into the initial stages when I actually knew about this, that there are two types of distribution of missing data, which is randomly distributed and structured missingness. So if the yellow marks are scattered without any noticeable pattern, it suggests that missing data might be randomly distributed, that there's no correlation between any of it. But if by chance it is structured missingness, if the yellow is clustered in a certain rows or columns, it might indicate a non-random pattern of missingness, which is very kind of good thing or also bad thing in some sense. For example, entire rows or columns might missing could suggest a data collection issue or that these features are not applicable in those cases. So you might not want to remove it, right? So these all are the very crucial decision which you have to tell. So now I've also written these have this number of a column, single missing values and all. So from all of this insight, what do we gather? What sort of issues to be addressed? The first one is we need to address the missing values. There are moderate missing values, there are significant missing values, or there are single missing values. So how do we address this? Maybe significant, we go ahead and drop these columns entirely as we don't have the data, they don't add a significant value, or we implement with some missing values. Moderate, in which we can put it in with some zeros for numerical ones, or maybe missing values could be filled with no basement or no garage for categorical. Depends on how we want to handle it. I hope you have seen feature engineering lectures, then it will only start making sense. And then we have single missing values. These can be filled with mode or mean for categorical. So we can just take mode and then put it in over there. Now we have also seen there are a lot of issues of outlier detection. Like there are a lot of features which has a huge outliers. And we also need to categorically encode it, because machines can never expect English. You need to categorically encode it. I hope you know what is categorical encoding. And then feature engineering. Based on the insights, certain features needs to be engineered, like combining related features, creating international terms, or because there are skewness, we need to also figure out how do we transform skewness to normal distribution, because regression works on the normal distribution, because it should be normally distributed, then only it will work. And then as I say, the correlation should be good. So we need to also see the multicollinearity, because this is one of the assumptions of regression. So we need to look at all of this, which we're going to look at in univariate, multivariate, and bivariate analysis. So let's go ahead and look at that aspect too. Until then, bye-bye. So now what we will do, we will go ahead and possibly do univariate analysis. So the reason why we are doing univariate analysis, because we have found that from the whatever insights which we had, that sale price is somewhat distributed. Standard deviation is 74,000. That means it is somewhat distributed, and it's kind of significantly distributed. It is not normally distributed. That is one. I want to know because for working of algorithm, linear regression, which we're going to use, you need to make sure that it is following normal distribution. So we're going to look at the distributions of our target variable and then possibly go ahead and see if there's something can be done. So we'll look at our distribution of our one target variable, and then we'll look at for categorical variables and stuff like that. So what I'm going to do, again, it is going to be probably the same design pattern which we're going to use. And over here, what we're going to do is we're going to create, first of all, an simple abstract class. Simple abstract class is strategy, which is univariate analysis strategy, and it will have a simple method, which is the analyze. So every strategy will follow this analyze method. It will take the data frame in because it is a univariate, which means it will do the single analysis, one column for only single feature, right? That's why it is univariate analysis. So it takes a df and then the feature, which is what feature to analyze. So it will ask these two information from the user. Then we create strategies. The first strategy which we're going to create is numerical univariate analysis, because we want to first of all analyze the numerical features. It is a subclass of univariate analysis strategy, and this is one of the strategy of that strategy abstract strategy class. Now here we'll analyze it. The analyze will take a data frame in and the features in. So data frame will be more like a pandas data frame, and the features will be more like a string. And then it plots the distribution of how it is distributed. It is normally distributed, positive distributed, negatively distributed, and stuff like that. So it eventually has this parameter and then the feature. And then we plot that. So we again figure 10 by 6 inches, and then you plot a histogram because you want to see the histogram. I hope you already know what these histogram are. We want to plot for this feature. We want to KDE is equals to 2. I'll explain you what this KDE means, and the bins equals to 30, which means I'll also explain you what these 2, 3 means. So we go ahead and plot that particular thing. So we import first of all univariate analyzer, which is this particular class, and then we give numerical univariate analysis because we want to do the numerical stuff, and then we click on execute analysis, giving the data frame and the particular column name. So when we do that, we get something like this visualizations for our target variable. Now KDE means that it is a kernel density estimate. It is a line. It adds a line to the histogram, which represents a smooth version of a histogram. Because if you see that this line which is going, it is a smooth version of a histogram, which better estimates the distribution of the data. You can better see it from here. Right. And the bins equals to 30 means that it specifies the number of bins or the intervals for the histogram, because you're having several intervals out here. So what should be the proper intervals? So which I've set to 30. So now let's say if you increase the more number of bins, which means that it will provide a more finer granularity for the distribution. But if you have fewer bins, it will show more coarser overview sort of thing. So if you want to look very in detail, then you increase the number of bins. But if you do not want to, then it's a coarser overview you will get. Right. So, but coming back to this, we create an abstract method. That abstract is a strategy pattern which has this analyze, and the numerical feature, numerical analysis is a subclass of this strategy, which is one of the strategy. And then you potentially plot an histogram, giving the title, the X label, and the Y label for the same. And then you click on plt.show, which means it eventually shows the image. We create another strategy for categorical features. So that this strategy is for categorical features indeed. And what it does, so it analyzes the categorical feature by plotting their frequency distribution. So over here for categorical, we're going to plot this particular count plot. So count plot is kind of a more specified version. So if I could show you, this is how it looks like. So we set the strategy. Instead of reinstantiating that class, we just set a strategy to categorical univariate analysis, and then we execute the analysis on this data frame for this particular column, which is neighborhood. And this is where you have several like names, Gilbert, Stone BR, names, Thomas, Biadel, and all these. So you get the count plot for this too. Same happens. What is the X? What is the data? And what is the palette view we want to have? What is the title? X label, Y label, and then at last show. So this is the this is what we use for analyzing the categorical feature. Now if I go ahead and show you what is insights which we get from the univariate analysis, it's more about that the sale price distribution. So the distribution for the sales price is positively skewed, because that's what I was telling, because most of the majority of the houses were falling between $100,000 to $250,000, which means that if you see over here, it is 100,000 to 250,000, most of the prices, right? So that's where most of the things lies in. And the peak frequency is around the 200,000 mark, which is the most number of houses are around 200,000 mark, right? $200,000. So what does it mean? That skewness suggests that most homes in the data sets are relatively affordable. Of course, it's 200,000 for the real estate is very affordable, with fewer high-end properties. There are very few, right? So it also suggests that the long tail on the right side, which you see, that's where your expensive items comes into play, and which may need a special consideration during modeling, right? So that your model looks at the high end prices too. So for that, if you have seen my feature engineering lecture, you must be knowing that we can possibly apply or use log normalization, log transformation to normalize this distribution to follow the normal distribution assumption of linear regression, right? So that's where another learning for you, that if based on the implications that okay, it is because there are some high-end properties, we could apply log transformation in order to normalize this, in order to follow make this follow one of the assumptions of linear regression. Now, as we move forward, there is another one, which is the neighborhood distribution, which is the categorical feature. So what does it mean? This shows a varied distributions being the most neighborhood, followed by college, CR, old town, and all. So the higher frequency of, now what is the implication of this? This is another understanding, is for the certain neighborhoods suggests that there are areas who could significantly influence overall pricing values. So if it is names, then it can overly influence overall. So it is the problem of imbalance class problem, because there are several areas which is lower, but you need to handle it very carefully. Otherwise, what will happen if there is problems of overfitting will start to happen, problem of not model being not able to intelligently recognize, overfitting will start to happen, because there are very few observations, because for the certain categories there are very few observations. So your model might completely focus on few observations which has the highest number of rows, right? So you need to make sure that overfitting does not happen. That's where you apply regularization techniques, or probably frequency encoding, and all those things comes into the play. However, we'll be not focusing too much on improving it, because there are a lot of things which will be given to you for sure by the end of it to improve it by your own also. So that this is something which you learn on the go. So this is what the univariate, where we understood our categorical, one of the target variable, and one of the categorical most important variables. You can do the same for other numerical features, other categorical features along the way, because for me it was more like that I wanted to show you that how your decision process thinking should be. You can go ahead, figure out, tweak it around, find more numerical variables, see what exactly, build a storyline on top of it. So what you can do, you can say that okay, if the price is this much, then you could possibly predict by taking on the mean, or looking at the distribution of other numerical features, right? So there are a lot of things which you can do into it. I want you to experiment it out by your own and see how it helps you. Now into the next one, I'm going to show you how you can compare two variables, which is bivariate analysis, and then see what it yields. Go ahead and learn a little bit about comparing two variables and probably seeing the relationships between them, comparing two features and seeing the relationships between them. That's what we call as a bivariate analysis. We'll try to follow the same strategy is the strategy pattern. So we'll create an interface, which is bivariate analysis strategy, which takes the data frame and is an input, feature one, and what kind of second feature to be analyzed. So these two features will be analyzed, and the method will visualize the relationship between these two particular features. So now we'll start implementing it. The first we'll implement is numerical values, numerical analysis, which is numerical versus numerical analysis, which means we'll put on y-axis numerical, x-axis numerical, and then we'll try to see the relationship between two of it. So it takes in as an input of a data frame, and then it pulls out a feature 1 and the feature 2, and we've set up the size, scatter plot. I hope you know the scatter plot. X should be feature 1, Y should be feature 2, and the data where it should take these features is the data frame which we ask for, and then we show. So the third step, as I told you, that we want to do the bivariate analysis. So we want to analyze the relationship between two numerical features, which is ground living area and a sale price. So we instantiate bivariate analyzer, giving them the numerical versus numerical analysis. And also we have already imported numerical versus numerical from that file. I hope you know then how to import all of this. You can look at the file that we have imported it, and then possibly we just click on execute analysis. We give the data, we give the first, we give the second. So the y-axis, so you just must know that sale price should be on y and ground living area on x. So now if you see that this is the scatter plot. So what do we infer from this scatter plot? How do we interpret it? So that's what it is written over here, that there is a strong positive correlation between the above ground living area and the sale price, that larger homes generally sell for higher prices, which also indicates that the data is correct because larger homes will obviously sell for higher prices, right? And over here, it appears to be very linear. That's what the model expects. If you see the thing is very linear, but there is one issue that there are a lot of outliers too. There are some outliers too, which needs to be looked at. So it validates the linearity assumption, considering that there are some values which is out of the linearity line. So we need to look at that aspect too. So the linear relation confirms that there is a strong relationship between the ground living area, above ground living area, and the strong predictor of sale price. So which means that if you give me the, so the model says that if you give me the above ground living area, I will tell you sale price with higher confidence, which means that it is a very important feature. But there is a presence of outliers which require a further investigation or may be treated or has to be removed from the data in order to avoid any potential concerns or issues into our model. So I want you to try out with more features. I want you to look at whether they are a strong predictor or not by looking at it, by looking at the sales scatter plot. So it helps you to better understand these paradigms. Apart from it, I want you to try that out, but we can also try out categorical versus numerical analysis, which means that we can have another strategy which can analyze the relationship between the categorical and numerical feature. So what does it mean? That we will first of all analyze it, and then we'll have a box plot. So what it does, it plots the relationship between a categorical and numerical feature. I'll further explain you by taking one example. So if you go here, by the way, this is the context class which sets the strategy. I have already explained, and executes the analysis by calling that dot analyze feature by the strategy which was set. So if I show you, this is what we are trying to do. We are trying to analyze the relationship between the two categorical feature and a numerical feature. So categorical feature is the overall quality of the house, which ranges from 1 to 10, and the sale price, which is our target variable. Now, if I could explain you what this box plot means, and of course I expect you that you already know some of the technical details of it, that x-axis into this represents the overall quality variable, which is likely categorical variable indicating the quality rating of houses, which ranges from 1 to 10. And the y-axis over here represents the sale price, which is the target variable, which is a numerical variable showing the price at which houses were sold. So what does this boxes indicates? Each box represents the interquartile range, IQR, so-called IQR, I hope you already know it, of the data for a particular quality rating. So for a 1, there is interquartile range. For the 2, there is an interquartile range. There's 3. For 10, there is an interquartile range, right? So the IQR spans from 25th percentile to 75th percentile of the sales price. And the line inside it, indicates the 50th percentile over here. So that's what the box plot is. I hope you know the difference. How can we interpret the 25th, 75th, and all. The whiskers, the line which we call it is known as the whiskers. It shows the range of the sales price that not considered outliers. So if the value lies over here, then it is not. But these circles are the outliers. Because these are outside of the whiskers. Which is the outliers into this case. So that's why we use box plot to analyze the outliers too. So the dot outside the whiskers represents outliers, which are sale price that are unusually high or unusually low compared to the rest of the data. Just mark my statement. The dots outside the whiskers, which you're seeing the circles, represents the outliers because the sales price that are unusually high or unusually low into this case compared to the rest of the data which is available out here. So what do we observe from this? So we see that overall quality rating increases from 1 to 10, the sale price also tends to increase, which means we also seeing a linear relationship. Because if we truly increase the number of rating, the sale price also tends to increase. That makes sense. If the quality of the house is good, then the sale price will also be very nice. But if the quality of the house is bad, then the sales price will be very less. So it suggests a positive correlation between the quality rating of the house and its sale price. So you can say that it is a very general statement to say that if the house quality is good, this is going to definitely, you're going to sell it for a better price. And then you can tell to the stakeholders that this is the price which you can sell it. That's where you use data science to make thorough data decisions. Now, higher quality ratings show a wider range of sales price, which indicates more variability in the sales price of higher quality homes. So, which you can see that there are higher variability into the high ratings house too. So I hope that you understood how can we analyze. You can take more, learn about correlations, how you can look at it, how you can build a storyline out of it, how you can help this to make the guys to make better decisions, and all sort of things can be inferred from it. So I've written the same over here that you can look at the quality out here and the answers out here, right? So whatever we have done, univariate, bivariate, missing, basic, what do we conclude? We conclude that both are strong ground living area, overall quality as very strong price predictors. These features should be emphasized on the predictive models. However, this is my inference. You must go ahead and try out because there are a lot of features. I want you to go ahead and try out that what features might be possibly the strong predictors of sale price, right? And then the data distribution, the positive skew of the sales price, and the wide range values of ground living area and overall indicate the need of careful data processing, which means that it does not follow the proper normal distribution which is needed for the regression algorithm, right? So we need to do the very nice transformation or normalization of our data. Another one is outliers. So outliers in this relationship between ground living area and sale price needs to be examined closely because, again, we do not want our model to not address this luxury home. So we want to also make sure that this has taken inside the data and model is learning from it. So I hope that this makes sense. Now we're going to the last part of our analysis, which is multivariate analysis. So let's catch that up in the next one. We'll get started with multivariate analysis, which is the last part of our analysis program. And so let's quickly go to multivariate analysis, and it is pretty simple. Again, it follows the same strategy pattern, a template pattern into this. So it defines the template for performing multivariate analysis out here, and subclasses we can override specific steps like correlation and stuff like that in order to increase it. So multivariate analysis will involve two things which we'll be doing. We'll be doing generate correlation and generate pair plot, because it is not technically possible to do bivariate by looking at, pair plot generates the overall summary of whatever happens with the features, how they engage with them, what is the correlation between them, and all those things which is needed. So that's why I love this pair plot, and heat maps will tell me everything which is needed, what is the correlation involved with each of these features with all the combinations out there. So I'll create an interface. The interface will look like this, that this will have a method called analyze, and then analyze will simply perform a comprehensive multivariate analysis by generating a correlation heat map and pair plot. So it takes in the data frame, whatever needs to be analyzed, and returns nothing because why? It's because maybe it met the method because it's more about orchestrating the correlation, and then that's it. There's no returning out here. Now we create the generate correlation by giving. So generate correlation is another abstract method, and the generate pair plot is another abstract method which we have to override. So we create, first of all, we do the simple multivariate analysis. There's nothing we'll do very, very complex. We'll start with the heat map. First of all, we'll generate a correlation heat map by giving the data. The size will be 12 by 10, and you just take out the correlation of it by core and annotation 2, CMAP equals to cool warm. All of this you can get to know as sns.heatmap. You'll be knowing each and everything. What does it mean? What does each parameters mean, and what do they expect in return? So I want you to look at the document too if you want to know more about the in detail and what sort of things can be involved into this as a parameter. The title, correlation heat map, and then plt.show. So it generates. So now on another pair plot, we could say that, okay, we need to generate the pair plot. So sns.pairplot, we just give the data frame, it will automatically generate the pair plot for the selected features, whatever, which is mostly the numerical feature which will be selected. So this is what the multivariate, we import the multivariate analysis, and then we go ahead into doing this. So we simple multivariate analysis, which we import. If you truly see in the top, we have imported it is from multivariate analysis, analyze.source multivariate, we should import the simple multivariate analysis. And then what we do, we simply select the features, because we just want to get for these selected features with numerical features, and then we analyze those selected features, because that will select the selected features out there. So this is what, to make it more simpler and understand, you can also change the selected features to make sure that you truly understand other features too. Now over here, if you truly see, if I could explain you what does really mean all these scatter plot and all. So the pair plot shows 5 variables into this, which is the sales price, ground living area, overall quality, total basement square footage, and a year built. And each row and column, let's say this one, represents the relationship between one of these variables, which is relationship between the variables of sale price and the sale price, right? So it will be possibly same. For the sale price with the ground living area is 0.71, right? So that's what it means. The diagonal which you're seeing everyone one, it shows the which is like more sort of 100% correlated, because sale price is exactly sale price. Ground living area is exactly ground living area. So the correlation between them is 100%. But the correlation between sales price and ground living area is 0.71, right? So all these things out here, you get the correlations and stuff like that. So say the scatter plot between sales price and ground living area shows the positive relationships which we have seen. And the living area, ground living area, what is positive relation? If that increases, if X increases, then Y also increases. This suggests that larger houses tend to sell for more prices. Same goes with sales price versus overall quality. So scatter plot between the heat map which is over here suggests that more the better the quality is, better the sales, more the sales price are. So just to come to this, blue colors represents the negative or low correlations, meaning that variables are not highly correlated, which also means that they're inversely related. And red color means that there is a highly positive correlations, meaning that variables are highly correlated with each other. So what does it mean? One indicates the perfect positive correlation, that they're perfect positive correlation, which means that as one variable increases, the other also increases at the same time. So sale price increases, the other sales price will also increase. Mostly they are same, right? -1 indicate the perfect negative correlation, which means that if one increases, then other decreases. But these are all the details which you have already had a talk. But coming to how do we interpret this? So let's say that sales price. So how do we interpret this sales price, correlation of the sales price? Sales price has the highest correlation with overall quality, which is 0.80 right now. So if you see overall quality with the sales price is 0.80, which means that overall quality tend to have a higher sales. So houses with better overall quality tend to have higher sale prices. Now, if you go to the moderated positive correlation, which is the ground living area or total basement square feet, which is, if you truly see total basement square feet with a sale price 0.63, and then ground living area, which is 0.71, which means that larger houses and houses with larger basements tend to sell for more. But the one sales price has a moderate correlation with the year built. For example, 0.56, that's what we call as a moderate correlation, not moderate positive correlation, but it is moderate correlation, which means that houses that suggest new houses tend to sell for more. That builds a good story, right? For that will also help your stakeholders to better understand. Same goes with, like, let's say ground living area. So ground living area suggests a moderated positive correlation with sale price, as we see 0.71. It also has a moderate correlation with overall quality, indicates that larger living areas tend to be associated with higher quality homes. Again, be very careful when I say this. So when I say this, that ground living area, if you compare that with overall quality, which is 0.57 into this case, which says a very interesting insight, that larger living areas tend to be associated with higher quality homes. That's one of the insight. Now, if you say that there is a low moderate correlation with total basement square feet and a low correlation with year build, which means it does not affect the sales price and all those things. So just like this, you can interpret for other correlations and make sure you build a storyline out of it. I've already built a very nice storyline. I want to look at the pair plot, scatter plot story, which I've written out here. You can write it in more detail. Now, this is the scatter plot which we have. I want you to understand it. So pair plot shows for, again, the selected features, and the diagonal plot shows the distributions of each variable, whatever the variable which we are having. Now let's try to interpret one by one. I'll not do everyone, but I'll try to interpret one by one. So let's say sales price to ground living area, right? So scatter plot between the sale price and the ground living area looks something like this, which shows a linear relationship. So it says that it increases, then the sales price also increases. Same goes with the overall quality. So now if you go to the overall quality and the sales price, this scatter plot shows overall a positive correlation. Positive correlation, which means that houses with higher quality tends to be more expensive. Now, if you truly see this total basement square feet footage, which says that the scatter plot shows again a positive relationships, but it is less strong compared to ground living area and overall quality. So these two are more important than this. So if there is a data issue, then you remove this instead of removing this. So all of this is helping you out. Year built. So shows that newer houses tend to have a better housing price, right? Same goes with other. If you truly see, that's how you can interpret other relationships and stuff like that over here itself by choosing right, what is the correlation, if it is positive, negative, inversely, directly, whatever. You just need to figure it out by your own. It is very easy to understand. So I took you some example. You can look at the pair plot, which is listed out here, answers to it, the nice stuff which you can see over here. Now, what needs to be addressed? Multicollinearity, feature engineering, and outliers. So, for example, over quality is an ordinal, which might benefit from it. So we just need to encode those overall. We do not want to treat overall quality because it just ranges from 1 to 10 values. So we want to ensure that this is more sort of a ordinal value rather than the continuous value. Another one is log transformation, because sales price is positive schedule and regression accepts some normalization. So we need to work on that. There are a lot of outliers too. So we need to work on that too. Multicollinearity, as I said, that linear regression expects that you need to have a normally distributed variable. So these three are the issues which we will address into our next set of lectures. So now we have analyzing done. We'll go towards this particular ingest feature engineering. Will work towards handling missing values, and then data splitter, model building, outlier detection, evaluator, and then we convert those things into ZenML pipeline, because we'll be once we complete the understanding of these, you have done core ML, and then we'll go ahead and try to integrate MLOps into it. So I hope that it makes sense. We'll catch up in the next one. Hi, so finally we are going to get started with making pipelines, making steps, actually model building, and a lot of things after whatever we have concluded from our insights. Because as I told, that we'll take another hour to finish this project, but our 1 hour just got spent onto analytics, which will make super easy for us to take decisions on what sort of methods we need to use, what sort of plan we should have. So that helps us to plan our future thing together. So that is why I love working on to analysis a lot, because as a data scientist, it is your work to spend a good set of time into working on it. So before going to that, I want you to first of all go into the ZenML document. And ZenML document is a very nice document, and now they have made it simpler, because when I was back in ZenML, I think things were little messy, and they were still at developing stage and the core stage. But now they have developed a lot and have explained the MLOps paradigm in a way that nobody could ever even touch. So that's why I always refer to whatever I can, and that's where we're going to use ZenML. And I hope that you have followed our PDF document, because please ensure it will not work if you have not followed our installation video. So I hope that you have your installation video ready, and that installation video should have your ZenML installed, your stack set up with MLflow experiment tracker and MLflow deployment, and everything should be ready into that, so that I do not so that you don't get error. Because once you start getting error, you'll start scratching your head and you won't get anywhere. So let's go get going ahead. And over here, I want you to first of all, if you don't know about ZenML, come here, learn whatever you can about what is the concept of pipeline, what is the concept of step. But I'm going to touch this in a very briefly basis. And what I could do is I could possibly, I may help you understand what is pipelines and what is steps are. So pipelines is like a pipelines. So kind of a series of steps. So you should first of all start with ingesting the data, then you should process the data, then you should handle the missing values, then you should handle the outliers, then you should handle. So it's kind of a step-by-step orchestration. So that's what pipeline means. Pipelines means you make a pipeline, in that you have step-by-step procedure to follow. Right. So into this, right, in case of my front, you have import, then profiling, and then train, and then go and evaluate. And all that happens under the ZenML pipeline. So I don't want to go on artifacts, models, parameters, and all, because I want you to look at it. But the concept known as local stack. So local stack, what does it mean? That over here we'll be using MLflow. I'll also tell you, I'll come back to this stack once again. But over here we'll be using MLflow for tracking our experiments and MLflow for deployment. And you want to tell ZenML that I'm going to use that, right? So local stack will have for Python orchestrator and artifact store, but also experiment tracker to be MLflow. You want to indicate those into your stack. So all of this is very important. So I'll come back to stacks once again so that you understand it. But before I want you to look at it and be very comfortable with what is pipeline and steps are. You can continue with this lecture, but I want you to be very comfortable with what these pipelines and stacks, all these things are. Okay, so now let's go ahead. What I want to do is go ahead and then start off with the planning now of the pipeline. So I want you to go to the training pipeline. So create a pipeline folder and go to the training pipeline. And the training pipeline, forget all the imports. We'll go one by one, okay, into this. You create @pipeline using a pipeline decorator. And then over here, you want to import model. So model is, which means that we're going to create a model into this pipeline, whose name is prices predictor model, right? So we create a unique model so that anyone can access the whole pipeline. We are just prices predictor name. So that's what I want you to first of all write it out over here. Of course, it is that you import from ZenML the model, pipeline, and step, and then you use that model and then name that as a prices predictor. So if you could go and check it out, it's kind of the model which, so that you in a pipeline you're having a model known as prices predictor. So we'll create a pipeline, definable pipeline, and this is an end-to-end machine learning pipeline. So any pipeline will have its first step, as what I talked. It's about data ingestion step. So we have already looked at the data ingestion step. If you go to the source file and then go to ingest-data.py, we have already completed this ingest data in detail. Now we need to convert this ingest data into a ZenML step. So how do we do this? We just go ahead and say that from source.ingest data, we want to import the ingest data factory, because factory is where you can switch your extensions. And then say file extension, whatever file extension. Right now we are dealing with zip file, so we say .zip, and then we say get data ingester, which is, and give the file ingestion, and then it ingests. So we just did this. It will act as a function which will take a file path as an input, and then we'll give the file path for to ingest, and then it returns the data frame. So you can see file path is string, pandas data frame is an output. Now we see the pipeline. We raw data is equals to data we just import from steps. This is a step folder. We import data ingestion step from the data ingestion step file. So you give the file path and it takes the .zip because it is an extension, and it calls .ingest, and then it ingests, and then it gets the raw data into it. Now the next step which we want to have is how do we handle missing values into it? How do we handle missing values? Because we have seen there are a lot of missing values into ours, so we need to also handle the missing values. So we have done with the ingest data. We'll go to the handle missing values.py, which is the source where all the logic has been written. Now I'll go step by step so that you understand it very in detail. Now, first of all, we import the logging. Logging is where it is a module to display log messages, because you can ZenML sometimes ZenML you cannot, in the pipeline you cannot have print whatever. You should have the logging system ready, right? Because logging is what ZenML uses it, and there are other like print, ln and all. So the logging module is configured to display log message with specific format. For example, we want to ensure ASC time, what is the level name, log, which is the log message, a log level, and what is the message, what was the tracking, so that it helps you in debugging. So that's what the configurations were set. Now, then you create an abstract base class that defines an interface for handling missing values. That's what we are trying to do, right? So it uses the ABC, module, which is abstract base classes, to enforce that any subclass must implement this particular handle. So the reason why we have this, so that any subclass which extends this must implement the handle. So missing values is kind of an interface. Now, if you go ahead, now this handle will take a data frame as an input and will return a data frame with missing values handled. The first strategy which we are having is dropping missing values. So it inherits the missing values, and if there's anything additional to take it, what access it needs to have. For example, over here, it defines whether to drop rows or whether to drop columns. So that's what access is needed, because we want to know whether to drop rows or whether to drop columns. In this case, we want to drop rows. That's why access equals to 0. And threshold, which means that the minimum number of non-values required to keep the row and column. So if the rows/columns with fewer than thresh values, then non-values are going to be dropped. Okay. So these are the access and thresh, and then you create, because it is mandatory to have the handle, it's a logging.info, dropping missing values with access and the threshold, df cleaned, drop now, you get the access and threshold you give because you have already taken as an input, and then you say logging.info missing values are dropped, and then you return the df cleaned. There's another strategy which is concrete strategy for filling up the missing values. So this class implements the handle method to fill missing values using various methods, either by mean, median, mode, or any value which you would like, which is known as the constant value, which you want. You can also put constant value 10, 11, 12, whatever you want. But the default method we want to use is mean, and fill value is equals to none. Right? We instantiate that thing, method and fill value, and then we make the handle class. So handle class is made as following, that we first of all copy the data, and if method is equals to mean, then you select the data types that you get only the numerical columns, and then what you do, and then you particularly go ahead and then fill the null values of that particular numeric columns with the mean of that column. Okay. Same goes with median, and same goes with mode. So, and if you have the constant, then you fill the null values with whatever, because it is none right now, nothing will be filled. If you put, constant, then you have to put something in here, otherwise the value will be none. So it either fills with mean, it either fills with median, or it either fills with mode or with a constant. And if this anything comes, if this another method somebody passes, then it says missing values, sorry, unknown method, no missing values handled. And then it says missing values filled. That's what it helps you in debugging, that you log every messages of it. And then what you do, you simply have the context class, which we usually do. So the class maintains a reference to a missing value handling strategy, which is a strategy that we have created an interface for, and delegates the task of handling missing values to it. It allows switching between the different strategies dynamically. So you can set the strategy and execute that strategy, which is handle missing values, which is dot handle. So you set so that you don't have to reinstantiate again and again to make this work, right? So this is an example usage that we take a data and then we say missing values, we want to drop missing values. So you just simply call dfclean.handle. Now you don't want to drop missing values. You want to follow the mean method to fill the missing values, which is you set the strategy and then you follow the mean method and then dot handle and then you give the data and then you get the df filled. So this is an example usage. What we're going to do, we're going to convert this into a step, which is the handle missing values step. So handle missing values will have this following. We first of all import pandas as PD. From source.handle missing values, we import drop missing values, fill missing values, and missing values handler, which is our abstract class. And then what it does, that it takes data frame as an input, and what sort of strategy is to have. The default one is mean. You can override it by median mode constant. And then it says if the strategy is equals to drop, then missing value handler will take drop missing values as a strategy and then possibly give that you need to only drop rows, and then it starts to drop rows. But if the strategy is mean, median, mode, constant, then you call the abstract class and then you say I want to fill missing value strategy with the method of strategy, and strategy which you have taken as an input, which is the mean into this case. Or else you raise value errors, unsupported missing value handling strategy, right? And then whatever handler is there, you just handler.handle missing values by giving it to the df, and then you get the clean df out from here. So then once you have this, you simply go into training pipeline which you have created and then fill the data and then you pass in just the raw data. So how it works, you simply go, you pass in your data frame, because strategy is mean, you don't want to change it, so you leave it on mean, and then it goes to your abstract class. Then abstract class sets the strategy of filling mean values with mean value, and then that executes with mean, whatever the code logic we have written, and returns the data frame with filled mean values. I hope that it makes sense. It is pretty simple to understand. It's just that it is a way to do it. I love this space, and probably I love the way it works out. And then now let's run it. So the way you can run it is you can just go ahead and then call Python run pipeline, right? So what it does, I just need to fix up some of the warnings because I'm using some sort of unsupported ZenML behaviors and all. So what happens that initiates a new run for the pipeline, ML pipeline. The new model versions was created, and it says models can also be viewed in the dashboard and all. So because I said that I use a stack of local, I hope that you have read the document on setting up this project first. So please set up the project first before continuing. This is the dashboard URL. If you truly click on it, you will be seeing this dashboard, and it says data ingestion step has started, and then it outputs a core data frame, and then it goes to handle missing value step, and it outputs a core data frame too, right? And then it says data ingestion step has started. Because I've already run it, it says we are using a cached version. You say step handle missing has started. It's using a cached version of this too, and it says it has been finished in following time. So we are done with this. Now the next step which we're going to do is we're going to do the feature engineering, which is log transformation, to make sure that things are normalized, and then we're going to work on the outlier detection step, which means that we'll detect if there's an outliers and handle those outliers, and then we'll split the model into training, testing, and test split, and then we train the model and then we evaluate the model. That's it. So that is the pipeline which we are looking at. So let's come back in the next one to talk more about feature engineering and outlier detection step. So hi everyone, let's come back to our project, and the project indicates that we have completed till handle missing value step. Now we have also seen that our target variable sales price were skewed, positively skewed, so we have to normalize it. There are several other issues like outlier detection and handling, and all those things has to be taken care of. So into this, we'll talk about two things, which is feature engineering and outlier detection step. So let's go to featureengineering.py, and into this, I wanted to look at this, which is we do our logging stuff same. We set our strategy, which is the interface for it, where we go ahead and then every strategy will follow a simple step, which is applying the which is a base class, which defines a common interface for all our feature engineering techniques or strategies, and any subclass must implement this apply transformation method, right? So there are specific concrete strategies. The log transformation, which is a strategy which is to be skewed features to normalize the distribution, because we have seen that sales price was positive skewed. So we will what we will do, we'll try to use log transformation also to implement that and out. Right. So log transformation can be used to reduce the skewness in the data, which means that if there is positive skew or negative skew, it can be helped to reduce the skewness in the data out there. Right. So what we could possibly do, we could write apply transformation, takes the data frame as an input, what sort of feature, because we want to indicate, we cannot just go ahead and apply transformation each and every stuff. We want to indicate which feature we should apply a transformation on. So we apply the transformation, we give in the data, it returns the data frame in return. So it says we are applying the log transformations to features this, it copies, and then it starts for feature in self.feature, because it is a list. We should apply log, which is by calculating. So log transformation, I want to look at it, it's more mathematical thing, but we simply apply the log transformation on top of it to reduce the skewness. So this is one of the strategy to handle the skewness and distributions, to make it normalized for our algorithm to work. Right. So another one is the standard scaling. Standard scaling, which means it transforms the data to have zero mean and unit variance. So you can actually use sklearn standard scaler. So right now I've just written this, but when we actually do the modeling, we apply log transformation on the sales target variable, because we want it to not change it too much. But for standard scaling, we'll be using our into sklearn only to implement this out, which is apply transformation. You apply .fit transform on the features, standard scaling get completed. Min-max scaling, same. However, I've just shown you for an example that how could we implement this. However, I will not go in detail about each and every, because it requires 1 hour another to explain you also this. So I want you to go and explore min-max, min-max and standard scaling. These are everything very easy. We have also taught a lot into the probability must mean regression lectures. So I wanted to look at it. It is so min-max, in short, it helps you to be between 0 to 1 and normalizes it for the sake of linear regression. So basically what we have did, we have just for the numerical, we have implemented log transformation, standard scaling, and then min-max scaling. Because we have also categorical columns, of course we are not going to use this thing. We are going to use sklearn formal sklearn thing. So it's more like we are going to apply onto all the features which are categorical, right? So it concatenates the transformed, because it also first of all gets the transformed, and then it drops the columns which are categorical and concatenates the column which are encoded. So that's what we have encoded right now by calling fit transforms, and then we get the feature names out of it to name the columns for it, right? So we have used one hot encoding. I hope that you have already known about one hot encoding. We have done that into the feature engineering part. So we do the one hot encoding and then it gets completed. So we create a context class for feature engineering, which means that it takes the strategy in, what sort of strategy, and then switches the strategy and apply the feature engineering. So let's say that you want to implement the log transformation. So log transformation is where we say feature log transformer, feature engineer, put in log transformation, what for sort of features we want to, these two features, and then you run that. You run the same for scaling, for min-max scaling, and for one hot encoding. So this is an example usage, but for our thing, what we will do, we will simply go to the training pipeline and just apply log transformation to these two features, which is ground living area and sale price. because they were skewed. You can also encode the values. However, I'll show you a different way to run feature engineering, because I'm not going to do encoding right now. I'm going to do encoding a little later. But now the next step is, now we have the numerical columns. How do we detect an outlier and handle it? That is another big question which we should ask. So if you go to the outlier detection.py, and same happens over here, that you import necessary libraries and then you create an abstract class which you must have this detect outliers, which will take data frame as an input and return data frame as an input. So we first of all we will recognize and then we will handle these two things, which we will do at right now. So over here, if you truly see z-score, so first of all, we're going to implement the z-score. So in a nutshell, z-score outlier detection is a statistical method which we use to identify outliers in a data set. So which means that we use the concept of standard deviation to determine how far away a data point is from the mean of a data set. So z-score is nothing but to know if there is an x data point, how far is that away from the mean. So if that is too far, which means that it is an outlier, but if it's too close, which is good, right? So we given a threshold. So if a data point z-score, whatever z-score we have appointed, is beyond a certain threshold, like way than your mean, then it is considered as an outlier. So I don't want to go again deep into maths, but the z-score of 0 indicates that a data point is at the mean. So what I could tell, and the z-score of 1 indicates that a data point is 1 standard deviation above the mean. So 1 standard deviation above the mean, whatever standard deviation variance you have. Then you have the further the z-score from 0 is, the more unusual the data point is considered, and then you can have that particular threshold in order to determine based on your business rules. So what I'm going to do is I'm going to have a particular threshold. So usually the thresholds, so you say thresholds are 3. So if the usual threshold which we have is either 2, 2.5 or 3, it depends on how hard you can handle, right? So I'm going to push out one of the data example, the way it works out. So over here, if you see, this is a sale price and the z-score for the sales price is minus 0.7595. So it is below that mean, but it is 1 point. So all these are outliers because our threshold is 3. But as soon as we set our threshold is 1, because we are too sensitive towards having an outlier, then this will become true because this is an outlier. So this is what this is what the z-score does. If you want to know more detail, I want you to do your research by your own and probably get things sorted on this part. Now, the same goes with IQR out. We have another strategy for detection, which is IQR outlier detection, which takes in a data frame and then figure out using the IQR. So IQR method is again same, like a box plot. So if any data point is above the whiskers, that's where or below the whiskers, that's what the outliers are. So how could I explain you? If I could simply say IQR outlier detection, and if I could show you, this is the way. So over here, this is the median, this is the Q1, this is the Q2, and this is all this whisker, all the points around this whisker are not outliers, but all the points above this whisker and all the points below this whisker outliers, the lower fence and upper fence, which we known as, right? So anything which beyond or below your lower fence and upper fence are outliers. That's what the, IQR outlier detection means, that we detect if they are above or below that whiskers, right? So this is another strategy for IQR outlier detection. This is one for using z-score, and then we create a context class that detects the outliers and handles it. So we first of all set this, we ask the strategy, what strategy which we want to use. And then we set the strategy by making that method. And then we detect the strategy by calling the detect outliers from these methods. And then we handle the outliers. The way we handle the outliers, if the method is removed, we remove the outliers by calling df.all. We just remove it, all the outliers from that particular column. And then if the method is capping, so what does capping means? Capping means that I just don't want to go in very detail, but in a nutshell, let's say this is your data frame, which is sales price and GR live area. So now this is far away from this, right? This seems like an outlier, right? So what it does, if that is an outlier, it will change the value of that outlier to a nearest data point which is not an outlier. Okay, so over here it converts that 2 lakhs to 1 lakhs, right? 10,000 to 4,000. So that's what the capping means into the capping outlier. So we also tell what sort of quantities we should have, the upper and the minimum, so that if anything goes beyond it, it looks out for the lower one. If anything goes above it, it looks out for upper one. What is the nearest one to it? And then it just changes the value. Right, so this is what the outlier detection is, and then you simply go to the training pipeline and then you clean the data outlier detection step. You give the engineered data, and then the column name is nothing but the sales price, because that's where we want to look at it. So I hope that it makes sense. Now the next step is data splitting and then model building. So you must be noticing why we haven't done any such encoding right now. Encoding we will directly do into the model building step, because that's where we could. I'll tell you why the reason when we do the model building step, because it is a big reason to tell about that. But before going to that, let's go ahead and then run this data splitting too. So data splitting, because we need to split the data. I don't want to explain it because we have already done a lot. It's just that because we want to also test our model whether it is performing good or not. Because if we truly train our model in every data, then if we just ask the same questions, then it already knows it will perform obviously better. So we just split the data into training and testing set. And then we first of all train the data, train the model on those training set, and then test the model on those testing set. So we go to the, so if I could show you the feature engineering step, it says that if the strategy is logging, if we create that feature engineering step, it takes the data frame as an input, the strategy, the features list, if there's anything needs to be there. If the feature list is none, then you say raise an error, right? If the strategy is log, you put in log. Strategy is standard scaling. If the strategy is 1 hot, you do 1 hot, and then you return your transformed stuff. And then outlier detection step. So it says received a non-type data frame. So we are saying that if the data frame should be must, it should expect a pandas data frame, then only it will work. It should make sure that a column is present in that particular data frame, and then it selects the numerical columns from that, and then it starts the outlier detection and returns out and handles those outliers, and it returns out the DF cleaned. It is self-explanatory. I don't want to go in very great detail, because that's what we have done right now. Is very simple. It just create conversion step and then call those functions and methods and classes over here to make this turns out. We are using z-score outlier detection into this case. Now, once we have that done, we go to this data splitter. So which means that it will return data frame, series, x train, x test, y train, y test. And yeah. So over here, you call it from ZenML and then import data splitter and then simple trains test split. So if you go to data splitter, we again try to make this very nice, is create an abstract class, split the data, because there are a lot of things might be coming. What must be the test size? You simply create the concrete strategy by having self.test size, random state, and split the data into the following stuff. And then you create a concrete class for that by setting the strategy and splitting by calling that stuff up. Data splitter step, you call that thing, and then you say strategy should be simple train test split. If there's anything complex, you need to, if you can just extend that abstract class to more complex strategy. And then you simply call that dot split, and then you give target column and the DF. It returns the x train, x test, y train, and y test. Now let's try to save it and we run it. Perfect. So let's go ahead. Very nice. So here you have data ingestion outputs. It outputs something, feature engineering, data splitter steps output these 4 answers, which is good enough. This is output 1. This is output 0. This is output 1. This is output 2. And this is output 3, which is correct. Good. So we are done with the data splitter, and the next one which we're going to focus on is building the model and then evaluating the model. And then we'll be mostly done with our system, mostly, hopefully. And then we go ahead and deploy the model and possibly, what do you say, test our model on top of it. Right, and then we mostly finish our project. So let's go jump onto the model building stuff. So now we come to the model building part, which is one of the most, I think I like this part too, and probably where I spend a very less my time into model building, because I spend most of my time into analysis, structuring, processing, and then because model building then becomes very easy for me. So we import whatever libraries. So linear regression, pipeline from sklearn. So this is one of the things which I will talk on, why we are importing these two. But this regressor mixin is the type of the model which linear regression trains, and then when it comes out, when you call .fit, it returns this regressor mixin. So we set up the configurations for logging, and then we create an abstract class. So abstract class is where your model building strategy comes into play, that we want to, that abstract class must be having build and train model method and any of the subclasses which it will have. So xtrain is the Panda data frame and ytrain is the Panda data frame, and it should return the regressor mixing, which is a trained scikit-learn model instance, not the untrained one, right? So you create a concrete class, first of all, linear regression strategy. So you train the model first by taking two inputs, xtrain and ytrain, and then you ensure, and then it returns a pipeline. So what it does, first of all, we want to make sure that they were both the correct types, a data frame and a series. So once it's there, we start that, hey, we are starting up with linear regression model. And then what we do, we create a pipeline with a standard scaling and a linear regression. What does it standard scaling means? If you have seen, I have only did scaling to two numerical features. I have not done to all. So to make things easy for me for this project, I'm going to use simple standard scaler, which is feature scaling, which we have also implemented the same. And then a standard scaler helps you to have the zero mean and unit variance. I want you to learn about it. So I'm going to use that very simply for other features out there. Whatever other features I have, I want to use standard scaling, which is what as standardly. However, you can go ahead and experiment it out with min-max scaling and other set of scaling based on the context. But for this context, standard scaling works the best. Then the standard, so now let's say that you do not, then you train the model. So this is the pipeline. Start with the standard scaler and then linear regression model, pipeline.fit, and then return the pipeline, which is the trained scikit-learn instance. Now you may ask me, hey Ayush, why we need to have standard scaler? Just why can't we first of all scale it differently and then train the model differently? Now let's say you give the ytrain. You give the ytrain, right? So you give some testing example. So that has to be also scaled to whatever your linear regression has learned onto that scaling. So let's say that if this linear regression has learned your scaling onto the scaling of this, only this can help, right? If you apply new scale, you instantiate a new class, a new standard scaler, then it might scale that to differently and model will lead to very differently. So it's a very logical thing, right? So if even any samples comes in, the trained, whatever standard scaling which is trained on, linear regression is trained on, they do that standard scaling on that only. Okay, so we call this .fit and then fit the pipeline. So it starts with standard scaling and linear regression. So model will first of all go through, so if any input comes in, the model will first of all scale it down to what it already learned, and then it trains, and then it actually predicts the model, right? .predict. Very simple. I hope that it is very simple because it is very crucial to also understand why I'm doing it. Because if you do not understand, then I want you to try out very differently. You will try to think logically too, that if this is different, then this, if new example comes in, then linear regression will expect the input the input which was scaled, which was feature engineered by this standard scaler, right? Not from the different standard scaler, from this only. That is why we have to make it in a pipeline in the sklearn. So the context class for model building, we first of all have the strategy. Now you can have multiple algorithms too. You can scale it down to polynomial regression. You can scale to L2 regression. So a lot of things which you can do it, scale it down. Because that will also be your assignment also, because you'll have to work on to these several other algorithms, compare it, make a proper report. So all those things will be given as an assignments to the students out there. Now, if you go ahead, you can simply go ahead and then the strategy which you have to follow, which is the model building, the type of the strategy would be because this is the subclass of the model building strategy, the type of would be the model building strategy. So you set the strategy of whatever, and then you build the model by calling the build and train model method. And that's it. That's pretty much it. Now you go ahead model building, and then you simply go ahead and create the step out of it. This is again one of, now we are also doing a lot of things over here in model building step. So we'll be also using MLflow now. So we'll be doing MLflow integration. So again, I'm going to say you, please make sure that your stack. So if you do ZenML stack describe, it should look something similar to this. Which is your orchestrator should be default one, experiment tracker would be MLflow tracker, and model deploy should be MLflow prices me, and the artifact store should be default. So this should be your stack. Then only MLflow will work. So over here we are going to import MLflow, import pandas as PD. We are going to import the regressor mixing because we want to indicate what the output will come, and then these two I'll explain you in a bit, right? And the pipeline, one-hot encoder, and things like that. So over here, what I have done is I have not used the model building from this file because of several reasons. Of course, I want you to use it. You can use it for sure, but I just wanted to have it over here only. So of course you can just change that fit to something else, but I want to walk through I want you to walk through my decision process. So my decision process was that the reason why I didn't use that because the pipeline over here involved couple of more things. I can also do it over here, but over there I want to also save that as an artifacts. I don't want to just save it over here. I want to save that as an artifact. You can also do over here. Both will make sense. But most probably I done it over here to just save it as an artifact. That's it. There was no intention behind me to again, do not use that model building and come over here. So of course I can also delete that if I want, because that does not helps. Now I wanted to first of all ignore all these things right now. Just come to this over here. If you remember in our pipeline, we have said model equals to price predictor. That's here we instantiate about what the model is. So model price predictor, what is the license of it, the description of it is price prediction model for the houses, and then this is the unique name to identify anywhere. Right, you can just call this price predictor. You'll be getting all the artifacts and stuff like that directly into the pipeline. Now we say that enable cache equals to false because as you have seen that it was using my caches. Experiment tracker, I will come back to this in a bit. Now it takes in X-train and Y-train, and then it returns in pipeline, which is a trained pipeline, which first of all scales the value, transforms the columns and stuff like that, and returns the sklearn pipeline. And returns the sklearn pipeline, and we say that is model artifact? Yes, it is the output of the particular step. And that's what the artifact config means. Artifact config means that we indicate that whatever output is coming is an artifact. Please remember it because we will be using it to train and predict our model. Use this to predict or infer our model. So first of all, we ensure things, and then because if you have noticed, we have still not converted our categorical columns using one hot. Why? Because I wanted to do it here because I want it to be an artifact config. So categorical columns, we select the data types for categorical and then for numerical as the same. If you can see, include object, exclude object. Then what I do, I simply, sometimes what happens, what I usually see, sometimes when doing stuff, we end up creating nan values all by ourselves. So we make sure, even though this may not make sense, you can also remove it, but we make sure if by chance anything comes into play, you just do simple imputer, which is impute the missing values with the mean of it. Right? We have did handle missing values, but if by chance anything happens, then you simply impute with the mean. Because I always like to be safe. And then the pipeline looks like this. Over here, we impute first of all from the simple imputer, which is the strategy which is the most frequent, which is the mean into this case. And then we one hot encode it. One hot encoding means, I hope you already know, because it is a bit of work to say. But here's what it means. That says ID 1 red, 2 blue, 3 green. So red is being created, color red, and then if it is there, then it says 1 either 000. So that is what the one-hot encoding is, that it creates a separate column. So it increases the features complexity by creating new columns for that particular unique variable, and then uses 0 or 1 to indicate whether that is there or not. Right. So that's what one-hot encoding is. And then what we do, we actually have this column transformer. So what does column transformer means? Column transformer means that we use a pipeline of simple imputer and one-hot encoder in order to combine numerical and categorical transformers. So over here if you have seen, one part is that numerical transformer where we are using this to impute missing values from mean, and there's a categorical transformer which is the for the categorical variables, imputing with the most frequent values, which is the median right now, and mode right now, and one hot to change from the English to numeric format. And then we want to run this together. So that's what the preprocessor means, the column transformer. The transformer, it will combines the numerical and categorical columns together to make the column transformer. So this allows steps to be applied to different subsets of the data all together. And then what we do, we simply define the pipeline. The pipeline is, first of all, this is the preprocessor that you first of all get through the numerical one, and then the categorical one, and then you train, and then you have the model of it. And then what you can do, you can simply go ahead and then log the info saying that pipeline.fit, which is the pipeline which I've created. So it first of all goes through the numerical columns and then categorical columns, and then it applies all whatever pre-processing steps, and then it fits the model on top of it, and then trains the model. And then because the categorical features will be lot. So if you print right now, you'll be having a lot of categorical features just like this. Color red. So we want to know what my model expects. We want to know what my model is going to expect. So after training, it logs. So by this, we just get the feature names out of it, which is the get feature names out of the categorical columns, which has been trained on. It logs the column that the model expects, which means that it is very helpful for understanding the input required by the model after processing, especially when using the one-hot encoding. Because then you can, I'll tell you why it is helpful in a bit, because we also want to know what columns which my models are expecting. So which are the columns which they have used to train our model on. Now that is one thing. Another thing is that we also want to do the experiment of everything. Like we run on this, and then let's say we change this to mean to median. So that becomes another experiment, right? So we want to also track the previous one and right one and compare it. We change this to another strategy. We actually use some sort of z-score and do something interesting over here. So whatever we could do, so we want to also extract every run which we are doing, right? So over here, what we will do, we will simply call from ZenML.client import client, which means that it instantiates get the active experiment tracker from the ZenML. Right now, MLflow is the active which is from there. So that's what we get, because we have also, it gets the active experiment tracker, and it says that we enable cache equals to false in the step decorator, and experiment tracker is equals to experiment tracker.name, which we have instantiated, the name of the active, and the model which we are training from. This is the model. This is the price predictor, so that your system is aware, because when we do the deployment, this is very important to know what model should I go ahead and deploy. So prices predictor is the model which I should go ahead and deploy. Right. So it says that if there's any current run, MLflow is currently running, please stop it. Right? Of course. If there's no current runs, then start the run. It starts a new MLflow run if there's already not running. And then if we use MLflow has a lot of available good features, but currently we'll be using sklearn.autolog features. So what it does, it automatically captures the model matrix, parameters, artifacts, inputs, everything and then it shows into the dashboard. So what I'm going to do, and finally we end the run once the things are completed, I'm going to go ahead and show you this in live. So the training pipeline, we have model building step over here. We split the data, model building step over here. I don't want to go to model evaluation step. Let's go to model building step right now. And also you can see that that prices predictor, because it says that your model which we want to deploy is the prices predictor one. We simply go and run the pipeline. So the run pipeline will look like this. So I'm going to just uncomment this so that you get the URI. Now I'm going to run this to show you, how it helps. Let's wait. I just hope that no new errors comes in. Perfect. So it says that your model evaluation matrix is following, your mean square error, which is very low, R square, which is very low. It also model expects the following column. You must be noticing that it had dropped most of the columns who are not relevant in outlier detection. So in numerical columns, the categorical columns, there are no categorical. Of course, there are some categorical columns at that point, but we have just used the numerical columns to go ahead and train it out. Model expects the following numerical stuff, right? And then what it does, it's simply, you can just go ahead and you can run this MLflow UI. Wait a sec, let's run this. Perfect. So now if we run this, let's open this, and this is the current one which we ran, which is the ML pipeline. I want to go over here, ML pipeline, which is just now, which we ran 1 minute ago. We click on this, and that's where you have what is the tags, what is estimator name, logged models, the parameters it is going to have, what is the matrix it is having, the model matrix, the system matrix, the artifacts, what are the artifacts, like ML model has been put in over here. You can see over here what sort of inputs it requires, what sort of outputs it gives, right? The PKL file, so that you can use this model to further make predictions on top of it. Now you can just go ahead and see our previous run too. So this is the previous run. So this is how you can track experiments over here for the pipeline. Okay, so this is how we use MLflow. This was not a very big deal. It's just that you need to put your little bit of mind into model building step and auto logs, a single line. That's why I call this ZenML very powerful, because it helps you to automatically log stuff and things, which is very helpful. You can also manually log things if you want to in MLflow, mlflow.log. Perfect. So the next step which I want to focus on is the model evaluator step, which is not so hard. I will skim through it very quickly. So what it does, it simply creates an abstract class, first of all, for model evaluation strategy. It expects the model, the testing set, and the testing for labels. And then it simply goes ahead and predict the model, and then it calculates the mean square error and the R2 score. And then you can set the strategy. Now you simply go ahead and the evaluator step and tests, make sure that things are all right, and then get the name steps and then transforms. First of all, as I said, that if you give this X test to the model, the predictions will be very bad. Why? Because that is not what the input the model expects. Model expects the pre-processed input, the scaled input, the categorical encoded input, and all those things, right? So then it initializes the evaluator with the regression strategy, which is the model evaluator, and then your strategy should be regression model evaluation strategy. And then we evaluate by we do not give preprocessor into it, we just give the model, because we have already processed our testing set. So we just give the model from not the preprocessor, and the X-test preprocess, not the directly X-test, and the Y-test of it. Okay, and then it prints out the mean squared error. That's it. So I hope that it makes sense. We simply go to the training pipeline. This is what it looks like. We call this model evaluator trained model, whatever model which we have created, and then it automatically takes the model from it by looking at by pre-processing first, and then the model, X test, and the Y test, and then finally it returns the model. So that's it about the whole training pipeline which we have completed. I want you to look at the ZenML dashboard. So let's go to pipelines. Let's go to ML pipeline and let's go to this one, the latest one. This is what the whole pipeline is. It starts from this and ends on the model evaluator step. Perfect. Now what we will do, we will go ahead and create the continuous deployment pipeline. The continuous deployment pipeline, which means now we will deploy our models. And then once we get that API, once the model is deployed, we'll be getting the local link, local API calls, which we can use that to call and make inference from our deployed model. So let's go ahead and then try that out and see how it works. Go to our final step, which is deployment and inferences of our model. Now that is an amazing aspect of ZenML that you can literally via some commands, some lines of code, you can literally deploy the model and infer it out from there. So what we will do, I will quickly make you go through some of the steps. Let me just quickly close all the stuff. Yeah. Now, if you go to the pipelines, we have completed the training pipeline. We are good. We were able to get the MLflow. Now I want to go through this deployment pipeline. So deployment pipeline will import ML pipeline, dynamic importer. I'll talk about what is dynamic importer, model loader, and prediction service and the predictor means in a bit. But what it does, it imports the pipeline from the integration from MLflow of steps. It imports the MLflow model deployer steps. So it uses the model deployer step to import that. So it is its own ZenML written step. You don't need to know the logic behind it. If you want to know, then you can go to the ZenML source code and try to. That's what a ZenML tries to simplify it for you. Now, if you truly see what happens over here is it simply goes ahead and then we make this following continuous deployment pipeline. So continuous deployment pipeline is decorated with this pipeline decorator, which indicates that it is a ZenML pipeline. And this pipeline is responsible for training the following the model and gets the trained model in return and then deploying it using the MLflow model deployer step. So it takes three things. This is already a predefined ZenML step specifically designed for deploying the models with MLflow. So it says that workers equals to 3. What does it? This parameter indicates that there are 3 worker processes will be used for serving the model. So if you call anytime, there will be 3 guys who will be always available for handling multiple requests simultaneously. So when serving the model, the capacity will be nice. The deploy decision equals to true, which means we want to deploy it, that the train should be deployed or redeployed whenever the pipeline runs. And the last one is the what model to be deployed, which is the trained model to be deployed over here. So the continuous deployment pipeline into this ensures that whatever ML pipeline is run and a model is trained, it is automatically deployed or redeployed using a MLflow. Then we have inference pipeline. So inference pipeline, what it does, it first of all loads the batch data. So what does batch data means? So we are using dynamic importer. I want you to first of all see the dynamic importer step. That is why we created a sample data for our model to make predictions on. This is the sample data which I've written. That's why I looked at the columns which my model expects. So that I can make the sample data. You can also take your X test to perform it. But I just taken for a sake of sake. And then I converted the data frame to a JSON string because that's what your pipeline accepts. So this is the batch data which I want to make it for reference. And then this is now I want to load the deployed model. So the function out here will load the deployed model for me from the pipeline name as continuous deployment pipeline because this was responsible for deploying the model into the server, right? And what was the step name of it? The step name of what that was MLflow deploy step. That is the one who deployed the model, right? So let's quickly go to the prediction service loader. And what does prediction service loader tells? So over here you have this following, which is responsible for loading an existing MLflow prediction services, which is already running because inference is what? Inference is making predictions once the model is trained, right? So inference is once the model is trained. So it is responsible for loading an existing MLflow things. So it expects the pipeline name and the step name where the model was used to. So this step is designed to be used within a ZenML pipeline. So you can retrieve the prediction service that has been deployed using MLflow via ZenML. Right, so we import following statements. We from ZenML integrations, we import this MLflow deployer and then MLflow deployment service. And then first of all, we go ahead and what these two things does to first of all give you clarity. MLflow deployer is a class from ZenML MLflow integration because they've already integrated it that manages the deployment of models using MLflow. And then there's MLflow deployment services, which is a deployed MLflow model service which handles the model inference requests once, which is like a more sort of a prediction that it helps you to make predictions. Right. Now over here, if we go ahead and then try to make you understand each and every step, which is the function, it retrieves an active model prediction service based on the pipeline name and the step names, which is over there. And then we get an active model deployer. So what it does, this method retrieves the active MLflow deployer component from ZenML's active stack. So that's why I tell the active stack should be there, right? So whatever stack is there, it gets the active MLflow deployer, which has been used to deploy the model. So this is used to manage the deployment and services. So once that is done, we get our model deployer, we get the active model deployer. Now we find the model, which is find model server. So this find model server from model deployer will look out for existing model services, MLflow model services deployed by that specific pipeline and in that specific step name, which is a continuous deployment pipeline, MLflow deploy step name, right? And then the result is being stored in the existing services, which is a list of MLflow deployment service representing the deployed model services, right? And then we say that if there's no existing services, then you say no MLflow prediction services was found. If there is, then you return the prediction service. So if there's an active service, then the function returns the first service, which is the best model being deployed, which can be used for making predictions. Now you can use that .predict, this service out there, right? So let's go to our deployment pipeline once again, and that's where we get our model, which is the trained model. Of course, we have to go and train first, and then you'll be running this. And then you run the predictions using that model deployment. So let's go to predictor. So this predictor expects the model which is trained on, which we get from the previous step, which is the prediction service loader, and input data, which is in this case the batch dynamic importer, which you have implemented the batch data. It returns the NumPy array of predictions. So it loads out, it expects these columns, and then possibly it converts that into a data frame, and then it converts the data frame to JSON list for prediction, and then it service.predict by giving the NumPy array, and then it returns the prediction, which is the set of NumPy array, right? So this is what the predictor is, that simply predicts. So now the next step is that we want to run this deployment pipeline, which is not so easy. I want to first of all explain you what this run deployment. So this is what the run deployment is. So let's go ahead and learn a little bit about what this run deployment is. Let me have a cup of tea. Yeah. So over here, what we are going to do is we orchestrate two ZenML pipelines. We run two ZenML pipelines. One is the continuous deployment pipeline, which trains and deploys the model, and another one is which uses the deployed model to make inferences. So what we will do, we will first of all import any necessary things. Click, which if you want to stop our MLflow prediction service, we can just call this, I don't want to further make any inferences from the model. That is what stop service will do. Of course, we won't do it right now. We'll import our continuous deployment pipeline and inference pipeline. And then we import from ZenML integrations get tracking URI, so that we know where our model is being deployed, right? And then what we will do, we will simply go ahead and then import this MLflow model deployer to deploy our models. Now this is that model name should be prices predictor, because this was the model name, if you have seen, that we have registered when we were training the model, right? So this is the uniquely way of taking the models in, right? Now the run this particular function will orchestrate the both deployment and inference pipe processes. Now let's go ahead and try to get you the answers to it. So if stop service is equals to, true, which means into this case, of course, it will be false. So we get the MLflow deploy stack component over here. So what does it mean? That if the stop service flag is provided, the script attempts to stop the running of the MLflow prediction service and then moves ahead into the training of the model. So MLflow deploy.active model deployer, this one, what it does, it retrieves the active model deployer component from the ZenML. So ZenML has its own deployer steps. So it takes it from there, which is get active model deployer. And then it finds the model server. So it searches for an existing model server instances based on the pipeline name, pipeline step, model name. Because we already know that it must be. So it is more like if your thing has already been not run, then this happens. But for the first time, this will be ran. So to better make you understand, if the stop service is if the things are running, if it is true, and you have already deployed the model, it simply goes and gets the existing services. That's it. By looking at find model server from this continuous deployment pipeline, MLflow deployment, what is the model name and all. But if it is not deployed, then it runs the continuous deployment pipeline. That is what happens in the first time. Second time, because the model is already deployed, it will not every time deploy the model, right? It will fetch the existing services unless there's no change in the code. If there's any change in the code, it will run the whole pipeline. So continuous deployment pipeline, what it does, it runs your continuous deployment pipeline, which eventually more makes the deploys the best trained model. But if it is already ran, then this script will run and it finds the best model server based on the pipeline step and name. Now we say that we just stop the existing services. For example, if the existing services is there, then we stop the existing services, which means if any active model is found, it just stops the service using existing services. So to make you understand what exactly it does, if the stop service is equals to true, then it stops the service of the current model. Make sense? But if it is false, most of the time it will be false, then it will continue like this. Continuous deployment pipeline, then model deployer, which is MLflow get active model deployer, it gets the active, and then it runs the inference pipeline. And very simple, MLflow deploy get active model deployer, it runs the inference pipeline and it gets to inspect. You can also run this track to inspect your experiments, and then it fetches the existing services with the same pipeline name, step name, and model name. So existing services, which is the trained model which is deployed now, right? So this is the trained pipeline. This is the step where the model has been deployed to, right? Then says that the MLflow prediction service is running locally and as a daemon, the process inference, we are accepting request at this prediction URL. You can go ahead and make your prediction URL a request on top of it in order to go ahead. But if you want to stop the service, you can call this stop service. So to summarize for you what we have done, if somebody says if it is to stop service, then it first of all fetches any existing services and stop it. But if somebody says no, then it continues. By default, it is false. It just go ahead and then runs the continuous. It gets the active model deployer, and then once it gets the active model deployer, it runs the inferences pipeline because the model has already been trained, and it fetches the existing services to make predictions by giving it the name of the pipeline and step name of the thing where the model has been deployed, and then it gives the predictions URL on top of it. So a lot of you have a problems in deployment. Why? Because you're not trying to get the core of it. The core of it is very simple, that if there is any change in the code which ZenML automatically understands from its past experiment, it will rerun the whole thing. It will rerun. And if that matrix is better than your current thing, then it updates the model. Otherwise, it does not. I hope you're trying to understand what I'm trying to tell. So this is the very basics of deployment is very simple. That you train the model, first of all, continuous deployment. If there's any change, it reruns. If you want to stop the service, what happens that it fetches the existing and then stops the service. But if you don't, then it continues running the continuous deployment pipeline, kind of trains the model, deploys the model. If the model is better, it shifts, if it makes the top model on top of it, and then it runs the inferences pipeline. In inference pipeline, what it will do, it will simply go ahead and then find the existing services, takes out the batch data, and then possibly go ahead and then runs the service.predict, and then it eventually finds the model server, whatever the model server is, and then you get the URL from it. Then you can use that URL to send requests to it and then get predictions for your model, which you can further integrate into Streamlit or any other application which you're building. It is as simple as that. Okay, so now what I'm going to do is I'm going to run it. Okay, but this time I'm going to run deployment.py. I hope it just works, because sometimes even to me it just skips dhokha. So it says predictor has starting services MLflow deployment service. Its start method completed. And now it says you can look at your experiments over here. And then you can also MLflow prediction server is running locally as daemon process and accepts inference request at this particular URL. Now, most of you say that, hey, I want to know about how can we integrate into Streamlit. I mean, it is pretty simple. If you have learned this, then this should be pretty simple. That you call this and then you send requests to this particular URL. So I'm going to say sample predict. And what we do, this is the URL of our MLflow prediction service where our model is being deployed. And then this is the input data, the sample input data. You can make it Streamlit by calling all of this. And then you just convert the input data into JSON format. You send the post request to the server, and it says if the response status code is 200, you take the JSON from it and then you print the prediction rate. If there is an error, you print the status code and the response from it. So it's just that sending the request by following the right data to it. That's it. You don't need to, need another 1 hour lecture, because a lot of YouTubers don't focus on or creators don't focus on the core aspect of it. They just focus on deployment on Streamlit. Deployment on Streamlit can be done by class 5th student nowadays. I mean, you guys are in college, so you should be able to get the API request URL and then use that to do something great, right? You use that to integrate in some complex stuff. But yes, integrating Streamlit is not a very big deal. So we just call this sample predict .py. And here we go, $280,000. If we give this, then $280,000 is the price of that house. I hope it makes sense to each and every people, and we are done. We are done with everything. We are done with most of the things. And I hope this project given you a sense of understanding of how things work and how things should work. We have done a lot of things. We ran a continuous deployment pipeline. So what is continuous? Continuous is more about if there's any change, ZenML automatically understands it. Right. So it runs a continuous deployment pipeline that trains and deploys a model. We ran an inference pipeline that performs batch predictions using the deployed model. We can start or stop the MLflow model prediction service based on the command line options. We can also inspect experiment runs and compare model performance using the MLflow model UI, which you can run this MLflow UI backend store, whatever over here. You can also see into your ZenML dashboard and everything over there too. Now, there is a lot of things to cover. There are a lot of things like E2E, batch, ETL, a lot of things we are coming up with into the course. I want you to look at it. We are done with this project. It was a simple house price prediction. While most of the people do it in just 30 minutes, we complete it in hours and get it done very nicely. So I hope you really like this project. Hopefully we come to the next one and we enjoy things out here. Is very simple work. What is the future scope of work? There are a lot of things which could have been done into the processing steps. I want you to experiment with standard scaling, min-max scaling, see how the how the things have been performing. So I want you to look at it, experiment it out, use MLflow experiment tracker to see the performance of the model. And then I want you to also focus on testing other assumptions of it and then seeing the performance of the model when you fix those assumptions. I want you to also try out several outlier detection things, because these are the core things which is very, very important, which you can run as a sort of an experiment every time. So I want you to focus on that too. Another aspect I want you to also focus on is the possibly, trying out other interesting feature engineering techniques, data processing techniques, new EDA things, so that you identify more of it. So a lot of things can be done over here. My whole aim was to show you the core aspect of it, an MLOps aspect of it. Now it's on you and how you can use it to make it the best project. Right now, this was not available on whole YouTube. This is not available on whole YouTube. So I want you to take this as an opportunity, do something great. We'll be catching up into the next project if I ever come across. Tab tak ke liye, I'll see you later. Bye-bye.